Ja, ja. Deze zou ook moeten gaan. Eén, twee, 1, 2, die gaat ook, hè.
Test, test. Ja, kijk eens aan. Ik kan gewoon... Ja, ik mag gewoon hier verder gaan in de slides en zo. Ja, oké. Voilà, kijk. Geen academisch kwartiertje.
Okay, good morning. Welcome to this PhD seminar. It's the second PhD seminar of this week. And also for the PhD students at ACRO, the second PhD seminar in 2 years. Last year, Due to Corona, unfortunately, we weren't able to organize a PhD seminar, but from now on, we intend to organize it each year. So today, or this week, all research groups at the campus are organizing or are participating in these PhD seminars. Today, it's the PhD students from Acro who participate, meaning that the topics will mainly be about robotics, mechatronics, and computer vision. Each speaker will have 20 minutes time to present his work or part of his work. So I ask the speakers to strictly respect the deadline. And then there is 10 minutes time for questions. So everybody in the audience can ask questions. Don't feel afraid to ask questions also to your colleagues. And then the people at home who follow this PhD seminar through the YouTube channel, they can also ask questions through the chat. And then we have people here monitoring the chat, and we will forward the questions to the speakers. So that's it. I don't want to keep you waiting. I wish you all a very interesting, inspiring day. And to the speakers, I wish you get a lot of tough questions, because you learn a lot, or most, from that. So good luck.
Yeah, thank you very much, Erik, for the introduction. Hello, everyone. My name is David de Schepper, and I'm a PhD student at Acro Research Group. And today I will give you a presentation about my research topic, and through this presentation entitled A Probabilistic Measurement Model for Radiological Sensors in Static Environments. So first of all, a quick introduction or a context what this presentation is about. So at the moment, the current operational nuclear power reactors are reaching their end of their operating life due to basically two explanations. One, old nuclear power plants are being replaced by newer power plants. For instance, in countries like Finland, that's the case. And on the other hand, the European Union and several countries have planned a nuclear power phase out. So, for instance, countries like Germany are already shutting down several nuclear power plants. Also Belgium, that's a bit tough, because it's also in italic font. So, so probably by 2025, some nuclear power plants will also phase out here in Belgium. And as a result of this, dismantling and decommissioning activities will increase in the following years and so on. So for instance, on the left, you see the nuclear power facility of Tihange in Belgium. And on the right, you see basically the new wave of nuclear power plants built in Finland. But before any D&D or dismantling and decommissioning activity can take place, a priori knowledge of the environment is key. At the moment, radiation protection officers are charged to perform in-the-field measurements, and these in-the-field measurements contain mostly three types of measurements. First of all, atmospheric contamination measurements. On the other hand, dose rate measurements, so for instance, ambient, so in the environment, or at a specific place, for instance, at a piece of wall. And thirdly, surface contamination measurements by direct method, so by swapping a piece of a wall, or by an indirect method, so without any contact. And due to the fact that these radiation protection officers are in charge to perform these in-the-field measurements, there are some severe drawbacks regarding to this. First of all, potential high dose rates can involve in those environments, and that's why the physical and also the mental state of these RPO personnel have to be monitored frequently, because due to these potential high dose rates, a risk of cancer increases, and also radiation diseases after a couple of years. Secondly, the manual process of acquiring these measurement data is at the moment very time consuming. It also depends on the size of the environment. For instance, if you have a small room, some measurements can take up 10 minutes each. But you can imagine if the environment increases in size, the measurements can take up to a few hours or a few days even. And thirdly, and that's basically what this presentation is about, these type of measurements are very prone to uncertainties or subject to uncertainties, for instance, in the adopted sensor, but also in the measurement angle, so the angle between the surface and the sensor device, but also in the post-processing of these measurements. So if the data is captated, it will be sent to a database, but in that process, yeah, some uncertainties are prone. So due to these many disadvantages that I've discussed in the previous slide, and high demand towards autonomous or semi-autonomous robots is seen. And these types of robots were firstly employed in the 1980s. So that's basically the first generation of robots that were employed in the nuclear scene. Most of them were teleoperatedly controlled, so using cable mechanisms, etc. But nowadays, research has focused on robots with cognitive capabilities. So basically dealing with these kinds of uncertainties regarding the motions, the environment they are operating in, but also the sensors, so the sensor fusion, etc. And this is basically pushed forward by the field of the probabilistic robotics, where these type of uncertainties are taken into account explicitly by using Bayesian statistical models. And that's also where this research or this presentation is about. We focus actually on deriving a Bayesian observation model for a type of radiological sensor and the usage of this model in state estimation techniques in static environments. So here you see actually a couple pictures of the type of robots that are employed in the nuclear scene. So on the left, you see basically the first type of robots. These were basically teleoperatedly controlled at Fukushima in Japan. And on the right, you basically see a robot that could be of Boston Dynamics. So basically a humanoid robot which tries to drill a hole in the wall, basically to decontaminate the environment or to rob a bank. I don't know. And these are basically the new types of robots that are employed nowadays in research. So on the left, you see actually a track-driven mobile robot, also employed at Fukushima, with a person on top of it. And on the right, you basically see a prototype of a robot that we have built together with some companies in the Archer project. So let's move on to the next section of this presentation. I was talking about a probabilistic Bayesian model, and what is basically a probabilistic observation model is basically a likelihood function, so P of Z, given X and given M, where Z presents basically a measurement from a sensor that can be a laser scanner or something, but in the context of radiological mapping and localization, it's basically a count rate measurement. X presents the pose of a robot. This can be a mobile robot or a 6 degrees of freedom robotic arm. And M is basically the model of the environment, so the map. And these models basically try to explain where a measurement is, what a measurement is. So basically, where do the probabilities come from? That's basically what these models imply. So for instance, in the past, there have been some developments regarding probabilistic models, sensor models for laser rangefinders. So this is basically a picture of it. This is basically a likelihood function where all the types of uncertainties regarding laser rangefinders in dynamic environments exist. For instance, we have a Gaussian peak with local sensor noise, let's say, but we also have a random distribution on top of it, basically for random measurements. Also, the max range measurement of a laser rangefinder can be found there, and also the unmodeled objects. That's basically the exponential at the beginning of this graph. And basically, this presentation looks at the research question: how does this likelihood function P of Z given X? How does it look like for a radiological detector? That's basically what we try to answer using this presentation. To do that, we have been inspired by previous work a couple of years ago involved in the derivation of such a model for laser rangefinders. But first of all, we have to look at what the data is looking at. So basically, the first step is to generate a data set using a robotic arm and a radiological sensor. As a robotic arm, we used our Epson 6 degrees of freedom robotic arm. So 6 degrees of six controllable degrees of freedom. And also, of course, a radiological sensor, namely a Chromec CZT gamma detector. So it measures gamma photons ejected or transmitted by a potential nuclear source. This Chromec device is basically mounted on the top of the end effector of the robotic arm, together with a 2D camera. This 2D camera is used to estimate the transformation between the Chromec probe and the camera frame. So, for instance, then we can estimate well the position of certain nuclear sources in a 2D environment. So these hand-eye calibration consists basically of taking several pictures with the robotic arm at several poses, and we fuse that in an algorithm, and at the end we can estimate the transformation matrix between a camera frame and a robot frame. So that's basically what it is. These Chromec sensor together with the robotic arm is then used to capture data at a variety of positions, where we can basically calculate the expected value of a measurement using this equation. And this equation is basically the inverse square law that can be found in radiation technology and nuclear engineering, etc. With the several parameters. For instance, A represents the detectable area of a detector. P represents the pose of the sensing device, and P of S represents the source pose, so that's basically the Euclidean distance that we have there. And E represents basically an angle efficiency, which we can look up using a graphical lookup table. So this is basically data from another paper where this angle efficiency is calibrated. And we have visualized this using a polar plot. So for instance, if a Chromec device is right on top of a point source, which has to be measured, then the efficiency is 1, but when the point source is basically behind the Chromec device, so this means a 180 degrees angle, then the efficiency of that measurement decreases to 0.6. We captured the radiological data using a Chromec ROS package, so this is basically a developed package that where we can communicate with a Chromec device using the robot operating system, and it's basically consists of 2 layers. First of all, the application layer, that's basically the low-level C++ API, which stands for the communication over USB 2.0 with the Chromec device. And on the other hand, we have the top layer, let's say, that's the robot operating system layer, which consists basically of 2 type of nodes, let's say. First of all, a constant publisher, which publishes data constantly at a fixed frequency on a ROS topic, and on the other hand, a ROS service, which can be called to measure, for instance, a count rate measurement or a full spectrum measurement. So we have captured 10,000 samples using the robotic arm and the sensor, and we can plot this basically in a histogram representation, and that's basically the result of this. So all the calculated expected values are around 38. So the histogram is meaned by 38. So every measurement is around 38. So this means that we basically have just one single distribution, a Gaussian or a Poisson distribution. And so based on the data sets that we have captured here and visualized using that histogram, in static environments, we can say that only the local measurement noise around the expected value of a measurement consists as an uncertainty. The next step, using that real data captured in the data set, is to basically learn the parameters of that model. And that's actually performed using a maximum likelihood estimation. So first of all, we say that our data is Gaussian distributed. So that's basically the likelihood function of a Gaussian distribution. The next step is to basically calculate the likelihood and then the log likelihood using this equation, and then maximize that log likelihood function using the first order partial derivatives and then with respect to our parameters, so the mean mu and the standard deviation sigma. So that's basically how we can calculate the parameters of that model. We can do the same with the Poisson distribution. That's this formula. Calculation of the log likelihood gives us this rule, and maximizing this log likelihood gives us, again, basically the same equation for the mean. And we know from the Poisson distribution that the standard deviation can be called or can be calculated using the square root of the mean. So given the model parameters, we can actually fit this model on top of the data. And as we can see, in gray is represented the real data set. In red, it's the estimated Poisson model. And in blue, the Gaussian model is basically fitted on top of the data. And as we can see, both models basically fit the data well. So we can say that basically both models can be used as the probabilistic sensor model for such a Chromec device. The small difference between the Gaussian model and the Poisson model is on top of it. So the mean or the mean peak is better estimated using the Poisson model than the Gaussian model. So using that model, we can perform some experiments. So the first experiment that we will discuss here today is the localization task of a single radiation source in a 2D environment using real data, real captured data. So the task is of given that model P of Z given X, can we localize a single source of radiation in that 2D environment? That's basically a state estimation problem. And as a state estimator, we use a sequential Monte Carlo method, or particle filtering, also known as. So these particle filter algorithm consists of a few steps. First of all, initialization of the particle. So one particle represents basically the state of a radiation source. So that means the 2D coordinates of it and the intensity of that source. And step one is basically the prediction step. But as we in this example, we don't do that prediction step because we have no uncertainty regarding motion. Step two is basically updating the weights by using the update step based on the measurements that we acquire, and then do a resampling, so we can resample all the particles into a new likelihood distribution. And this is basically the algorithm that we have used, that I have explained before, but I will skip that. And here is a visualization of the start of the state estimation problem. So the amount of particles that's a parameter that we can choose. For this example, we used 2,000 particles as several hypotheses for the radiation source location. The blue dot in the picture represents the actual robot position, or the position where data is sampled using the Chromec device. The black dots represent the estimates of the hotspots or the nuclear source location, and the big red dot is actually the true hotspot location. So I hope this works. Yeah. So here you can see an iterative, the particle filter is actually an iterative example, or an iterative algorithm. So in the beginning, all the particles were spread, but as long as the measurements are acquiring, we can see that the bunch of particles actually spread around the actual radiation source. And as we can see, the blue dot is going over all the 2D environment, which means that there is a possibility that other sources can be in the environment. But as the state estimation problem concedes, and all measurements are acquired, the state estimation converges to the actual, or close to the actual hotspot location. And the small red dot in the picture is basically the estimated or the particle with the highest weight that's visualized in this picture. And when we basically make a heat map of all the data, then we can see this representation. So actually the actual hotspot location was located on X 5.5 and Y 11.5. So basically the state estimation converge quite closely to the actual hotspot location. So we can conclude that our model works in a state estimation framework. All right, last slide, I think. Conclusions and future work. As a conclusion, a probabilistic sensor model for a radiological gamma detector has been derived, validated, and implemented based on real data that has been captured in a data set. Next, the model can be integrated in a state estimation framework, as we saw a couple of slides ago. As future work, we have also seen during the dataset sampling that when the sensor is moving, sometimes random measurements can occur during this dataset captation. And this means that basically if we captated that data, extra components in the model are arising. So basically random measurements can occur in data processing of measurements. So that's also a thing that we have to take into account in future work. Second, as future work, we propose the implementation of that sensor model for multiple source localization. So as a first step, we have seen in the previous slide that it works for a single source localization, but what happens if we adapt this model in a state estimation technique for multiple sources? So that's basically also future work. And thirdly, we would like to integrate this sensor model as an input for an active sensing framework. So basically, the measurements that were acquired were basically randomly chosen, and active sensing opts at minimizing the amount of measurements, and also, on the other hand, information gain. So the least amount of measurements to make sure that your nuclear source is localized closely to the actual position. That's also a third thing, future work. Okay, this ends my presentation. Thank you for your attention. And if there are any questions, don't hesitate to ask them. Yeah. Okay.
On slide 17, you showed that the robot was scanning the whole 2D space, but are you planning to investigate other strategies to converge faster to the actual hotspot instead of scanning the whole space?
Yeah, that's a really good question. As I mentioned in my future work slide, so the third aspect is basically the active sensing framework. And the active sensing means that less measurements can be acquired, but the information gain can be increased. So the purpose is actually to not scan the entire environment, because that's basically done by radiation protection officers right now. But as future work, we would like to integrate that active sensing framework together in the sensor model to make less measurements than radiation protection officers are doing right now, but increasing the information gain. So basically less measurements, but higher information gain in the location of the source, or potentially sources.
Thank you.
Any other questions? Yeah.
In your future work, you had it about the multiple source localization. Do you have some expectations about how it will look when you are not a single source, localizing a single source, but a multiple source? Do you expect something already before that you start investigating?
Do you mean that any a priori knowledge has to be added towards it? No. So basically, in future work, the state estimation technique that we try to use for multiple source localization assumes that there are no information is available about the environment. So that's basically an exploration strategy that we have to conduct. And basically that sensor model can give an answer towards that. So for instance, if we expect, if we get a measurement from our device, which implies with our sensor model, so we expect that, a source is located at another position, but we move towards another position, and we get a different measurement than we expected, and we could say that there are potentially multiple sources. So that's where the state vector of the state estimator will increase in size. So when that, so for instance from 1 to 2, and then if everything applies for 2, then we know that there are 2 sources in the environment. But also if the next measurement is not what we expected, and according to the sensor model, then potentially multiple more sources are available in the environment. Okay. Yeah.
So maybe just to add to the question of Raphael, that only works, of course, if you have an idea what is the value of one source. Can you explain on that?
So the state estimation creates particles, and these particles basically are randomly spread at location, but also randomly spread at the potential intensity of a source. So that's basically a 4-dimensional vector, 3D position and the intensity. And if you go iteratively through that state estimation technique, already as shown in the figure, then the hypotheses of all the particles will be updated based on the measurements. So for instance, if we say, so these particles basically don't have the information about the intensity of the source. So, and iteratively, if new measurements are acquired, then the intensity of the source is estimated better. But as we saw in this GIF, that when the red dot is basically on the right of our 2D environment, that the particle filter estimates that there is potentially another source in the environment. So basically 2 dots or 2 blobs of dots right here is presented or are available in the environment. But as we can see through acquiring more measurements, that the state estimation converges only to one source. So basically, this approach can be applied to multiple sources. I don't know if that's is an answer to your question. Okay. Vragenvuur zeg.
Yeah, maybe it's a good suggestion to, from this question I get that in the movie you could also visualize the intensity of the source and the estimated intensity, so that's maybe an improvement that you could do on the movie. I was wondering, in the movie the uncertainty on the source location doesn't go down. Is there, or doesn't seem to go down at least, while you're taking measurements. And initially I see this shape, okay, this banana shape, this circular shape, that disappears, that's okay. But later on, the uncertainty ellipse doesn't really shrink. Why is that? I would expect that it goes down. But. And second question is, there is also a lot of background radiation. How did you take that into account?
To go back on your first question, that the uncertainty on the location of the source doesn't decreases. Actually, it does because, but all the particles are basically visualized in that in this setup. So all the black dots represent a potential hypothesis of a potential source location and intensity. But for further improvement, I should imply that the intensity of the estimated intensity of the source is also given a color, for instance. But it actually does not decrease. So it's actually, but because there are a lot of particles, so 2000 that are plotted on top of each other, then it visualizes big, but actually it doesn't. Then your second question about the background radiation. So this background radiation is also the formula that I've used to calculate the expected value of a measurement here. Basically, we have to take a sum of the background radiation into this model or into this expected value calculation. So this is only for one source, but there's also background radiation available through nature, etc. So basically another component of this formula would be the background. And so that's basically also that has to be incorporated into that calculation. Okay.
Yeah.
Okay, yes. Okay. Good morning, everyone. I'm Yanming Wu, a PhD student from ACRO. My research is titled Multi-Object Tracking Framework for Human-Robot Collaborative Assembly. In this presentation, I will first show a short introduction about my research, then the 3 research objectives, then the progress on the first objective, which is 60 object post-tracking. Finally, I will show the future work. Let's get started with the context. So traditionally, the industrial robots are usually put behind a fence. During the robot operation, the human operator has to keep a safe distance, which is far away from the robot. This makes the collaboration of human and robots impossible. Nowadays, there are more and more robots which can work side by side with the human operators, which makes they are called collaborative robot or cobot. With the advancement of this hardware, human-robot collaboration becomes possible. In this video, you can see an example of a human and a cobot working together on assembling a automotive component. So the feature of HRC is that the human and the robot share the same workspace, and they work on the same process simultaneously. Also, the robot should be able to anticipate the human intention and dynamically planning its own tasks. The target is to reduce the human idle time and increase the task execution speed. To make this human-robot collaboration happen, we need a powerful multi-object tracking framework. So first, the robot needs to locate and manipulate the assembly components. Then we need the 60 poles for the assembly components. And then to anticipate human intention, it needs to know what is happening in the environment. So it needs to know the trajectory of multiple objects. And in this environment, there are two types of objects. First, the assembly components where the CAD availables are usually available. And then there are other objects, such as assembly tools, where they usually do not have CAD models, or it could be other unknown arbitrary objects in the environment. And there are multiple challenges to implement this multi-object tracking framework. So first, the assembly components could have multiple states during the whole assembly process. After combined with another component, its shape will change. And there could be hand occlusion while the operator is manipulating a component. Also, there could be prolonged occlusion by human body or arm. And we also have the real-time requirement. The robot has to react fast to process the environment information. And lastly, the 3D model of some objects are unknown, such as the assembly tools. Then we need either to treat them as a category of objects. So during training, maybe you can feed some samples of the power tools, and then during testing, you don't need the exact model of the power assembly tools. Or we can treat them as arbitrary unknown objects. Given its initial state, we just try to use this information and try to locate it in the following frames. To fulfill these functionalities, we define 3 research objectives. First, we need a model-based 60-pose tracking method for the assembly components. Secondly, we need a model-free 60-pose tracking method for the assembly tools. Then thirdly, we need to combine them and form a multiple object tracking framework. This framework should handle also the initialization of multiple objects, tracking result verification, and it should maintain the trajectories of each object. It should also handle the data association of multiple instances of the same object which have the same experience. It should also handle the prolonged occlusion. In the existing literature, for multiple object tracking where the trajectory of each object is required, most literature focus on the pedestrian or car tracking, which only have 4 degrees of freedom. It can only rotate along the direction of the gravity. Because for those objects, there are already very powerful detectors, so you can already detect multiple cars, pedestrians in a frame relatively fast. So you only need to do the data association between consecutive frames. But for 6D pose tracking, the pose estimation, the detection of multiple objects with 6D pose, it's taking longer time, and there are not many real-time works on that yet. And then in the field of 6D object pose tracking, most existing methods assume the 3D model is available, but in practice, that's not always the case. So this makes model-free tracking has more usability in practice. Also, the existing datasets do not reflect the challenges in human-robot collaboration. In HRC, usually the objects could be freely movable by the hand, but in the most popular 6D pose tracking dataset, YCB video, it has multiple static objects and the camera is moving. Then the pose distribution will be totally different from where the object can be freely movable in the space. And then in the lava dataset, where the objects are moved by hand, each sequence only has a single object. So we are missing a multiple 6D object pose tracking dataset. The last gap in the literature I found is that there's not an efficient way to combine the detection and tracking. So the temporal tracking is fast, but it's local. The detection is global. It can detect new objects, but it's slow. So we need to find out a way to leverage the temporal information globally. But I'm still exploring that. Now I would like to introduce my PhD progress on the first objective, which is model-based 6D object pose tracking. For this for this task, the input will be a 3D object model and the pose in the first frame, and a RGBD image sequences. The output will be the 6D pose in all the following frames. And based on how the information is used, there are 3 categories of methods. The first one is energy minimization based method, which define a energy function of the 6D pose and the measurements, and try to find the 6D pose by minimizing this energy function. So it's basically the ICP and its variance. The second category of approach is learning-based, which you try to learn the 6D pose from the data directly. Traditionally, the learning method is random forest, where you sample some points from the object, and by looking at how the points location change, you predict the 60 pose. And then nowadays, most methods use convolutional neural network to defer the 60 pose from images directly. The 60 pose tracking approach can also be seen as a probabilistic tracking approach, which transforms it to state estimation problem. In this table, you can see the performance comparison on the YCB video dataset. So the RGF is robust Gaussian filter approach. This one is based on particle filter. This one, SE3 TrackNet, is based on CNN. And the post-RBPF is based on the particle filter framework, but use the convolutional neural network for to evaluate the likelihood. So you can see that the CNN-based method has the highest accuracy with this metric, and it's performing real time. It has highest speed, while the Bayesian tracking approaches are relatively slow, not capable of real-time processing. The reason is that the measurements in this case, it has large dimension. The image dimension is large, which makes the measurement size large. So the computation takes longer. To select a method for further benchmarking, I decided to choose a CNN-based method due to its real-time performance and its high accuracy. I decided to choose this method, a framework for evaluating 6DOF object trackers, because it's evaluated with an interaction scenario where hands manipulating the objects, and it has state-of-the-art accuracy on the lava dataset where camera is static and objects freely movable. Also, it has the potential to track objects which are not seen during training, and it has a runtime of 6 milliseconds on this GPU. So deep learning methods are known for requiring large amounts of data. And to get the 60 pose of an object in each frame, it's a very difficult task. So this approach totally uses synthetic data. So it uses an image pair as input, and the output is the pose change between this image pair. For the first image, it first randomly sample an initial pose, P0, where it render the object with OpenGL with this pose onto a black background at a fixed lighting condition. And also make sure the object is always in the center of this image. And then for the second image pair, it rendered the object onto a diverse background with different lighting conditions. By sampling the P initial and the delta P, we can form 20K samples and use it as the training data set. The output is just their pose change, and then use a mean squared loss to train the network. During inference, when given the previous pose, we can also render the synthetic image the first synthetic image is rendered with the previous pose, and then we crop a bounding box in the current image with this previous pose and use it as the input for the second input, so that we can get the pose change between previous frame and current frame, and then by adding it to the previous frame, we get the pose in this current frame. So in reality, there could be occlusions in the frames. There could be different kind of noise in the environment. So during training, we use data augmentation techniques where the hand is superimposed onto the object to mimic the occlusion condition. And here the mean filter is added. Here the noise is added to the HSV space. And also here the sensor could be totally not working. So here we also put all RGB channels pixels to 0. Here shows the training plot of the model. So the blue curve is the training curve, the red curve is the validation curve. After about 25 epoch, we got the minimum mean squared error. And with the best model, we have a 4 millimeter translation error and 2-degree rotation error. Then I test this pre-trained model on a sequence where the clock model is augmented onto the image with the estimated 60 pose. In this case, it's only rotation and there is no occlusion. So you can see the augmented clock is very close to the real clock. In this sequence, you can see the scenario where there is horizontal occlusion. Yeah, it's hard to see where the exact clock is because it's occluded. But I think the performance is also quite good. And then in this scenario, the clock is manipulated by a hand. At sometimes now you can see the border of the original clock in the image. So that means the estimation is not very accurate, but overall the performance is also very good. After that, I also, so to verify if my reproduce steps are correct, I compare the results for each sequence with the results in the paper. So the paper is evaluating the performance for all objects, and the numbers shown here are the average for 15 objects. But I'm only showing the performance for the single object, the clock. But you can see I got comparable or better performance, so I think the reproduce steps should be correct. Then I try to evaluate this method with custom object. I first evaluate it on a yellow cylinder, which do not have many textures. So most of the time, so until now it's working well, but when the rotation speed is higher, the tracking could get lost. Yeah, you see now. The tracking is wrong and it cannot recover. Then I also test a object which has relative more textures, the power drill. So I test in the Z direction, X direction. And also did some rotation. So it's tracking better, I would say. But since it's larger, so I'm not moving it fast enough. Then I also tried to test how it works on larger interframe motion by processing the first video for every 2 frames. Then you can see the performance becomes worse earlier. Yeah, it becomes worse earlier. To conclude, this method requires a textured 3D object model and it requires an initial pose for tracking initialization. In terms of performance, given initial pose, it can track accurately when the interframe motion is not large, and it's also capable of real-time tracking. I got the call processing takes 8 milliseconds per frame with the 2080 GPU. The limitation is that it can only track single object. For each object, you have to train a separate network, and the CAD model is required during testing. Also, when the interframe motion is large, the performance drops, and there is no confidence score or uncertainty indication. So when it gets lost, you don't know when to reinitialize the tracking. So based on the second and third limitation, I got an initial idea for a possible improvement is to combine the convolutional neural network with an unscented Kalman filter, where we use the pose tracking result from CNN to get the pose, so that we can crop the RGBD data to the point cloud of the object, so that we reduce the measurement size, which makes real-time potentially possible. And also with this method, we can use the motion model to predict the pose for next frame. Then instead of rendering the first frame with the previous pose, we can render the frame with the estimated pose, so that if the estimated pose is closer to the actual pose, then the interframe change will be smaller, so that it can work better. This is just an initial idea which I will work on it further. And I will also evaluate the 6D pose tracking method in a HRC scenario. And after that, I hope to look into the model-free 6D pose tracking. That's it. Thank you for your attention. Thank you. Yeah, okay.
tracking tools, objects which don't have the cat model available. Is that right?
Yes, that's
Like a power drill. But yeah, the power drill or a hammer or screwdriver, these are quite similar, but not exactly the same. So I was wondering if you use things like domain randomization to cope with these small changes between power drills. As some power drills differ in the shape of the handle or the color, could you use domain randomization to cope with these differences?
yes, that's correct. So the question is, why? So I'm proposing to look into model-free methods, but sorry, it's Martin now. You, Martin, sorry, but Martin is asking, is suggesting that I can. The power drills, the assembly tools, they are quite similar. I can use some. I can during training I can give it some samples of power drill so that I don't need the exact power drill model during testing. Yes, that's also what I'm considering. By meaning model free, I'm just saying that I will not use the exact model during testing. So you can either treat the object as an arbitrary object without any prior knowledge except the initial state. But you can also, if you already know the category, you can also say, I want to track power drill, I want to track screwdriver, and during training you get some samples of those power drill or screwdriver. Yeah, that's also, then that would be called category level post-tracking. That's also one direction I can explore. Then the model free will be a level higher than the category level because then you have don't have any knowledge about the class. It would be class agnostic and also model free. I might look into both methods. Yes, for category level, then I will need a data set with a certain amount of power drill or a screwdriver or hammer, something like that. Yeah. Raphael is asking whether I'm using pre-trained model or I'm training from scratch. So I'm training from scratch. This method, it has the training script, but it does not provide pre-trained model. So it also does not provide the training data set. So I generate the data set with the data set generation script myself and then train it with the train script. And then also there's no testing script, so I read a testing script. So basically I have the whole pipeline, so I can, given a 3D model, I can generate the data set for training any object. Yes. Yeah, for now, that could be a direction. But for now, I don't have a concrete idea of how to intelligently combine them. So for now, I can only think about a combination of object tracking and hand tracking. I didn't see a more intelligent way to process this information yet. Yeah. Okay. Yeah.
Thank you very much.
Thank you.
Is goed. Staat die aan? Test. Ja. Hello everyone, I'm Ivar Dekker, also a PhD researcher at ACRO, and I'm going to present to you my PhD research named Isolator 4.0, Robotics within Isolators for Pharmaceutical Applications. This is a Bakelon project in collaboration with Pfizer Puurs. First, to paint a picture of the situation as it is right now, the isolator setup is basically a fully automated production line in a box with gloves on the side, which are used for if something goes wrong inside the system, a human operator can put his hands or her hands in the gloves and resolve the issue, or if some sampling has to take place inside the system, an operator can then proceed and perform that intervention. But this system has a couple of severe drawbacks. First of all, of course, safety. Because it's a human operator, safety comes as the first priority. So when an operator puts his or her hands in the gloves, the line is put on hold to ensure that nothing can go wrong. But this also means that there is a lot of downtime if interventions take place. Secondly, because we are working in a pharmaceutical environment, sterile integrity is of the utmost importance. So the gloves are a weak link in the chain because they need a lot of checking to ensure that they are still completely sealed and the sterile integrity is not compromised. Thirdly, because humans have to operate with the line is designed in a way that an operator can reach each part of the line he or she has to, meaning that the line is designed around humans and not around a most optimal line design. And lastly, there's a new upcoming norm, Annex 1, which is going to standardize the use of steam sterilization instead of the currently used hydrogen peroxide decontamination, which would not be possible with gloves due to the increased pressures and temperatures coming with steam. This project can be subdivided into 4 major work packages. First of all, there is fast, predictable and collision-free path planning, because of course the robot has to move inside the system, and of course preferably without knocking anything over or bumping into the wall. Secondly, there is a vision-based anomaly detection system and task management algorithm. So the system can recognize if something goes wrong, and if there are multiple things at the same time, so it can determine in which order it has to execute certain tasks for the most optimal sequence of tasks. Thirdly, we are planning to integrate an intuitive teleoperated control system. As you can see, our goal is to make 80% of the interventions fully automated, with 20% of the interventions via teleoperation. Or if something goes wrong, an operator could take full or partial control of the robot to resolve the issue manually, so to speak. And lastly, of course, all these elements bring new design changes that have to be incorporated into the isolator. So the fourth work package is a new design for Isolator 4.0. On the image here, you can see, excuse my rather poor photoshopping skills, but you can see a visualization of how this would look like. So you have a robot inside the isolator with a vision-based system for detecting the different things that can go wrong or to inspect what's going on, and then a control panel, for instance, as an intuitive teleoperation system. Of course, as a robot is capable of performing highly complex tasks, it brings a couple of benefits to the table. As the robot knows its environment, it's possible to perform certain or all interventions while the line is still running, as the robot can anticipate this and there is no real risk for safety without a human operator. Secondly, a robot action is completely traceable, recordable, and checkable. So if something were to go wrong, the actions of the robot can be saved and then later checked to see if it was actually the robot's fault or if there's something else in the system that went wrong. Furthermore, because we are working in a pretty critical environment due to sterile integrity and laminar airflow, operators are not allowed to move, for instance, too sporadically or too fast, but you can already feel that a criterion, what is too fast in a movement. So whereas that's for a human operator, that's a difficult parameter to take into account. For a robot, if you say to a robot, you're not allowed to move faster than this or with an acceleration greater than this, then the robot normally will oblige to that, unless, of course, there is a bug in the system. But in normal situations, the robot will take that into account and not go over that limit. Some major constraints of the project. The environment that the robot has to work in is rather small. So there is a limited free movement space for a robot to work in. And more importantly, as I said, there are laminar airflow regions in the system which flood the most critical components with sterile, clean air to ensure that they are free or completely free from contamination risk. And these airflows cannot be disturbed or cut so that once, for instance, the robot would move over a laminar airflow system blocking the airflow to the components, that could mean that the components have a small risk of contamination, and therefore the batch would have to be rejected, which of course is not desirable. This project started on the 1st of January of this year, so our first goal really was to close the loop for one intervention as fast as possible. We took a look at different interventions, as there are many, some reoccurring daily, some reoccurring only once a year, and we tried to figure out which intervention would be the most interesting to start with. And we decided to go with the intervention of a plunger which is positioned incorrectly in the feed. A plunger, basically a little rubber tip which is there to seal the vial of medicine, for instance. Why did we choose this intervention? For a couple of reasons. First of all, the different steps that the intervention is made up of. We think that that many of these steps are well automatable by a robot. For the rest, we think that this intervention has a lot of overlap with different work packages. There, for instance, is a bit of design for a tool that the robot can use, but there's also path planning involved for the robot to move to the plunger. Laminar airflow has to be taken into consideration for this intervention, and of course there's also an anomaly detection system which has to find the plungers that are positioned incorrectly. And lastly, this intervention for a human operator is actually one of the most complex in the list of interventions to perform, as there is a lot of precision and accuracy required at longer ranges inside a laminar airflow region. For a human operator, there's a lot of room for error here, with potential contamination risk. The rest of my presentation is built up around this intervention. So to start off, there is an anomaly and we have to detect it. So I tried this with 2 different systems. First, I used MVTech Halcon, which is a paid vision software to find the anomaly using a shape-based matching principle, where you basically make a region of interest of the thing you want to find, and then Halcon makes a model out of this and tries to find that model in different images. This method works rather fast and robustly once everything is set up, but it also has a couple of downsides. For instance, Halcon is of course a paid software. It's pretty expensive. It's license-based, and therefore it's also basically a big black box. We don't know how Halcon makes the model or what goes behind that model. So we can't make any alterations to that, but one of the benefits of it is that this method is more robust or less prone to things like lighting changes or scaling factors than the next approach you'll see, which is the same type of approach in OpenCV. But instead of a shape-based matching principle, I use template matching, which is very similar, but instead of making a model of what you want to find, you're basically taking a small image of what you want to find, and then OpenCV will pixel per pixel search images for this model or image and give a correlation score, and if the correlation score is higher than a certain percentage, for instance, you can say there's a match. This is a fairly easy approach. It's quick to implement, but of course it's more prone to lighting issues or scaling. But it could be further expanded with other image processing techniques like canny edge detection, for instance, to get closer to something that Halcon is doing. So now we have detected something that's wrong, but this is now only known in the 2D coordinate system of the camera and the pixel coordinates, so it's not something we can use yet. So the first step from here is to calibrate the camera so we can transform this 2D XY position into a 3D world pose. And the first step here is to perform an intrinsic camera calibration to calibrate the intrinsic parameters of the camera, which are things like the scaling factor, which is often 1, but if this is not the case, then of course you have to take this into account. The focal length of the camera, the principal point, which is where the center of the image is positioned, and if this is not in the middle of the image, then there's a skew factor which has to be taken into account. And lastly, the lens that is used with the camera can bring distortion of its own, like fisheye or pincushion distortions, which first have to be corrected before we can get any useful information out of the image. In Halcon, a camera calibration would look something like this. These are 9 of the quintessential images that you need. So 4 of them, the first 4 images are the calibration object just lying flat in each corner of the image to cover the entire field of view. Then there are 4 images where the plate is rotated around the X or Y axis of the plate to put the plate in a skewed or angled position to the camera. And lastly, you need an image of the plate elevated in the Z direction to give some more depth information. Of course, more images are always better, but these are 9 that you absolutely need to get a proper calibration. So once the calibration is done, we now know a 3D pose of the object that we want to find, but the robot does not know where this is yet. The robot doesn't know where the camera is. So to link that up with each other, we need to perform a hand-eye calibration, much like David explained in his presentation. But unlike in David's presentation here, we have a stationary camera known as a eye-to-hand calibration, where we basically fix a calibration object to the tool of the robot and then move it in the camera frame, taking pictures and trying to recognize that calibration object so that something like OpenCV can put a pose on the calibration object where it found it. And then you can take the pose data that's of course, the robot controller gives you to link these up with the following homogeneous transformation chain. You can then find the transformation of the camera to the base of the robot. So the red one, the camera to calibration object, that's found by something like Halcon or OpenCV. The green one is the one we want to find. The base to tool transformation can be read from the robot controller, and the offset to the calibration object is a fixed translation, for instance, which is the same for each pose normally, so that's a value you can just give in. So once the hand-eye calibration has been done, we can now translate the 3D pose that we originally found by the camera to something that the robot understands and knows where to go to. So the next step is to take that information and give it to a path planning software. We use MoveIt, which is an open source path planning or software package offering a lot of often used path planning algorithms like rapid random trees or probabilistic roadmaps. But for the first step here is to create a virtual environment of the real life situation with all the static collision objects that the robot could come into contact with, so the planner knows what to take into account and what to avoid. For a planner, we decided to use a probabilistic roadmap or PRM planner, with the main argument being that it's very good for static environments. This is because it's a multi-query planner which operates in two phases, really. So first you have a map building phase, where the planner samples the environment and creates nodes in it with collision-free robot states, but doesn't generate a trajectory yet. Once this map is built, it can then quickly link up these nodes to give a possible trajectory. The map building phase can take quite a long time, but the benefit of a roadmap planner like this is that the map is reusable for each planning attempt, and therefore, if the environment remains static, is a rather fast solution. But one downside that we also found when using a planner like this is that it can often find weird and convoluted trajectories, which if a human would be looking at it, would say that's not a logical trajectory to take. That's very long and windy to get to a movement like that, for instance. So we try to improve this for pose sequences in a static environment with a multi-threaded approach, with the goal of reducing variation on the trajectories themselves, but also on the total time needed to execute the entire sequence. And we compared this multi-threaded method, which we called repeated PRM, with just regular sequential PRM planning and PRM star planning, where PRM star is an optimized version of PRM, which will converge to an optimum and will on its own try to find a more optimal path, but does this at the cost of more computational power required and therefore taking longer. To give you an idea of how much longer a regular PRM planner with the map build will take about 0.5 of a second, for instance, to find a trajectory, whereas PRM star can take somewhere to 5 seconds to find a trajectory before it can be executed. On the graph, you can see that we tried, or we tested this for pose sequences of 1 up to 8 poses, and that the repeated PRM method showed an improvement over both regular PRM and PRM star, with the improvement over PRM star being rather consistent, but also rather large, and regular PRM being smaller but increasing as the pose sequences also increased. On the box plot, you can also see that the variation of the longest and shortest planning times that were found in the total set of attempts is also smaller than both regular PRM and PRM star, indicating that also the times that are found for each trajectories are more consistent. This image shows the visual trajectory lines that are being followed by the robot, also showing that the repeated PRM method shows a more consistent path that is being followed for the different attempts, whereas regular PRM and also PRM star appear more different for each attempt, especially PRM, but also PRM star. In this video, there's a example of a motion planning environment where I simulated a robot on a 7th axis alongside a transport belt, for instance, where it, of course, has to take all the collision objects into account, so it's not allowed to collide with any of the gray objects. But I also added a transparent red collision object, which the robot is not allowed to collide with, but the tool of the robot is. And I did this to try and simulate something like a laminar airflow region or a restricted area zone where the robot is not allowed to enter, but the tool, for instance, is, so it can still perform interventions or handlings inside that region. Lastly, this is a video of the demo of this intervention where everything comes together. So first there is a Halcon detection using that shade-based matching to find the plunger that's mispositioned. Yeah, the sound is still on, my apologies. So Halcon finds that plunger that's upside down and then translates it to something the robot understands using hand-eye calibration. Then that pose is sent to the planner, which plans a path collision-free directly above the plunger that has to be removed. And then the robot only has to follow a Cartesian path, moving down into the plunger and then scooping it out of the rail, as you can see now, to remove it from the system. My apologies for the sound again. Then to finish future work, the first step, I think, is to automate more interventions. Firstly, to show off different things the robot can do in the isolator environment, but also to move towards that task planning algorithm so different tasks could occur and the robot can on its own determine the best strategy and sequence to execute them. And lastly, of course, the teleoperation system for if something would occur that the robot can't do on its own, then an operator can take control of the robot and try to guide it or do it completely manually. Thank you for your attention. If there are any further questions, then feel free to ask. Okay. Mm-hmm. Yeah, the question is which part of the research and the packages so far was the most challenging to perform. So far, for this intervention, the biggest emphasis was on path planning and anomaly detection. And personally, I found that the anomaly detection and especially the calibration of the robot is something that, with a lot of challenge, there's a lot of things that could go wrong or that don't go according to plan, whereas the path planning section has a steep learning curve in the beginning, but once you're able to work with it, it goes rather quickly, so to say. Well, of course, I can't say that with complete certainty because each part has its own challenges, but I think the different interventions have different difficulties of their own. Some are more focused. For example, one of the interventions is handling Petri dishes. So one of the major path planning there won't be that big of a driving factor, whereas a gripper that can grab the Petri dishes, for instance, without squeezing it or breaking it and handling it robustly is a bigger challenge for that one, or later on there is also an intervention for delining a tub, which is basically a bucket which contains the vials which have to be filled, and the delamination is then removing the top paper cover. That also has challenges in vision, for instance, where it should open it, or how to handle that. So I think that different interventions show different challenges, and it's maybe now quite difficult to exactly say which one will be the most difficult.
So your major contribution to the PhD will be about the combination of all techniques?
Yes, it will be indeed the system that can then operate via a robot instead of a human operator. Hmm?
You showed a video about the plunger manipulation.
Yes.
Is this the actual speed it's currently running at, like an automated system, or is this the limited speed for the airflow?
So the question is if the speed that everything operates in the video is the actual speed that will be used at. Currently, this is just a speed that we chose for also safety reasons in the testing environment. For the real speed, that has to be determined later, of course, via simulations, for instance, to see at what speed the robot could move in the laminar airflow without disrupting it, or creating turbulences in it. So this is not it could be, but it could also be a different speed at the end.
Is the LBA, the airflow simulation, also something you plan to do in the PhD, or is this something someone else is responsible for?
Yeah, the flow simulation part, I honestly don't know yet if that's going to be part of my own PhD, as flow simulations, of course, are a topic of their own. But yeah, it could be, but I have to say that I don't know yet, sorry.
Will you operate in the same glove box as the robot, or occasionally enter the same glove box as the robot?
No.
If so, how would you cope with that?
So the question is if the human operator will work in the same environment as a robot, if I understand correctly. But the isolator is a completely sealed off system, so the operator would always have to be on the outside and look into it. So then, of course, indeed, there's the question, how will the operator look into the system, maybe via a glass plane, or a camera system, for instance. That is something, indeed, that has to be looked into to see what would be most ideal. Currently, the isolators are transparent, so an operator can look into it from the outside, but maybe moving towards steam sterilization, that's no longer possible.
So of course I'm aware of multiple applications or use cases afterwards, but do you think all of them are feasible with one robot, or do you see also opportunities to put multiple robots in the isolator which can work together?
So the question is if there's also some interventions that could benefit from a multi-robot setup, and I think that that's certainly something that could be interesting in the future. Also, as the line has two sides to it, of course, and you have that laminar airflow in the middle, a robot could not just move over the line to grab something on the opposite side. So for that, for instance, for that application, it would be useful to have a robot on each opposite side of the line to solve interventions that way, or certain interventions which could benefit from one robot holding something and the other one manipulating what the other robot is holding. So I think for certain interventions, there's definitely a benefit in using, for instance, two robots in the same environment. Yes.
See the plunger, I exert some force on the plunger and then it doesn't move
Mm-hmm.
until the static friction is gone, and then it only moves a lot.
Yeah, yeah.
Stops again,
Yeah, so the question is if in the video you saw that the plungers, the plunger that was removed was quite sticky. And this is basically a fault of my own because the plungers have of their own a grease coating to prevent them from sticking to the stainless steel rail they're in. But I was using rather old plungers in this video because I also at that point wasn't aware that they were coated with grease. So they were rather old and didn't have the coating anymore. And therefore they were rather sticky. At a later point, I also tried this with new plungers where the grease was still present, and then this problem was pretty much mitigated.
Okay. Good morning, colleagues. My name is Jeroen Kramer, and I'm a PhD researcher at the Department of Mechanical Engineering of KU Leuven. The research I would like to talk about is titled Simulation-Driven Parameter Study of Concentric Hallbach Cylinders for Magnetorheological Robotic Grasping. Nowadays, one becomes aware of the growing, uncertain and dynamic environments in manufacturing industry. To cope with this, the functionalities of the conventional industrial grippers need to be enhanced by implementing soft deformable structures. Soft grasping is divided into 3 principles: grasping by controlled actuation, controlled stiffness and controlled adhesion. This research focuses on controlled stiffness. This controlled stiffness consists of enveloping the target object softly and then subsequently stiffening the structure so the grasp is secured. It is also divided into granular jamming, low melting point alloys, electrorheological and magnetorheological materials, and finally shape memory materials. This research is narrowed down further into MR fluids. This fluid will, in the presence of an external magnetic field, change its aggregation state from a free-flowing liquid to a viscoelastic solid and vice versa in a couple of milliseconds. This fluid consists of micron-sized, magnetically permeable particles suspended in a non-magnetic carrier medium, typically carbonyl iron particles in a mineral or silicon oil. In addition, various additives are added to prevent particle settling and wear caused by the abrasive particles. The mechanical strength of this fluid is attributed to the formation of linear chains of particles along the external magnetic field lines, and the stiffness and the corresponding yield stress of this fluid is adjustable by varying the magnitude of the applied external magnetic field. Dus although MR fluids have already proven their usefulness in various applications, such as in shock absorbers for vehicles and constructions, the applications in robotics, and especially in robotic grippers, is promising, but is still there are still pending challenges. And for this, a number of research tracks are further improving the rheological, electromagnetic and mechanical properties of MR fluid, as well as improving the mechatronic design of these MR hybrid devices. And this research offers an answer to the latter by deriving guidelines to to get an optimal design of magnetic activation mechanisms to activate MR fluid as a force transferring medium in a robotic gripper application. For such a magnetic activation mechanism, electromagnets are often regarded as the only option to obtain a controllable magnetic field. But a vast number of turns and a large wire cross-sections are needed to get similar magnetic flux densities compared to permanent magnets. And at these flux densities, active cooling is needed to cope with the high electric currents in the wires of the electromagnet. On the other hand, permanent magnets possess a high flux density per mass unit and can provide more or less free energy. But in order to use such a permanent magnet as a controllable magnetic field source and to use it in a robotic gripper application to obtain and release a robotic grasp, the magnetic fields need to be adjustable. For this, in literature, Björk et al. Has simulated 5 different designs of permanent magnet assemblies. And they concluded that the concentric Halbach cylinders could provide the highest magnetic flux density in the cylinder's core for the least amount of magnetic material. Such a single Halbach cylinder consists of individually oriented magnet segments assembled in a circular way. To adjust the magnetic field inside the core, a relative angular rotation is provided to both cylinders. For a dipole, which consists of one pole pair represented by the bold arrows, this means an angle of 180 degrees, as is shown on the figures. It can be switched on and off. For a quadrupole, which consists of 2 pole pairs, this means an angle of 90 degrees. This permanent magnet assembly, this magnetic field source, the concentric Halbach cylinder, possess a number of useful benefits, namely a nearly homogeneous magnetic field, the need for little to no actuation forces to get the relative angular rotation, and it's also a compact device, since regulating the magnetic field inside the core will not change its external dimensions or shape. It has also proven its usefulness in industrial applications, such as magnetic refrigeration devices and nuclear magnetic resonance apparatus. This research presents a cylindrical radial bellow gripper filled with MR fluid. The green rubber membrane inside the hollow core of the gripper is actuated by pressurizing the MR fluid in its liquid state via the purple fluid inlet. A magnetic activation mechanism, more specifically 2 concentric Halbach cylinders, is provided at the outer circumference of the gripper's housing. It's the yellow and the orange circular part, and it's guided by an orange axial bearing. The angular rotation is provided by a worm drive. It's the black part. The worm wheel is attached to the movable outer cylinder, while the inner cylinder is fixed to the gripper's housing. The core and the membrane of the gripper are dimensioned in such a way that axial objects such as transmission shafts could be grasped with a diameter ranging between 10 and 58 millimeters, according to the Zimmer's RG1060 commercial compressed air variant. The choice for a worm drive is that compared to regular spur gears, a worm drive is considerably smaller, transmits a higher torque due to its high reduction ratios in one stage, and it also eliminates back drivability of the outer cylinder during rotation that's caused by intramagnetic forces. And then finally, as you can see, the Hallback mechanism is segmented, which is necessary in a practical application, that the Hallback mechanism is segmented in individual segments, but it will reduce the maximum theoretical achievable magnetic flux density inside the gripper's core. This research differs in such a way that we implement square segments instead of annular segments that are often used in literature. The square segments need to kept in place by a non-ferromagnetic cage. We have chosen for a square magnet since annular segments are less commonly available and require special manufacturing, so it will increase the production cost. Now, to compare single Hallback cylinders with each other, a dimensionless area fraction of the magnet area to the core area has been derived. In literature, static applications are often investigated, where the mass and the dimensions of the Hallback cylinder is of minor importance. So small area fractions, so large area fractions can be employed. But for our dynamic applications, such as robotic grasping, the mass and the dimensions are crucial, since they affect the dynamic forces and the moments of inertia. So small area fractions lower than 1 are recommended. In this research, a Python framework has been developed that automatically configures and simulates various Hallback mechanisms in their on and off states in parallel. The multiphysics software CSC Elmer has been used to carry out some 2D or two-dimensional magnetostatic simulations, and the post-processing and visualization is done by the Kitware's Visualization Toolkit VTK and the Python package Matplotlib for this research. But as future work will show, by implementing informed search algorithms such as HyperOpt, this whole optimization process could be automated without user intervention by installing a feedback loop, but more on that later. The performance of the Hallback mechanisms during simulation are characterized by a multi-objective function, which consists of a linear combination of 4 quantities, namely the mean magnetic flux density in the on and off state, the magnetic fields in homogeneity in the on state, and then finally the total area of magnet segments for both cylinders. But to make a fair comparison between these 4 quantities, normalization is crucial, and it can be done by the 4 displayed formulas. Then finally, to configure the importance of the 4 quantities, a weight factor is introduced, and the weight factor is set in such a way that a proper magnetic operation of a compact Hallback mechanism prevails over a homogeneous magnetic field. This slide features the complete data set for simulating the Hallback mechanisms, and thus the parameter ranges are also displayed. Then this slide shows 2 figures with the multi-objective value as a function of the number of square segments, the total area fraction lambda, and the relative magnetic permeability of MR fluid on the left-hand side, and the internal grasp diameter of the gripper core, the radial bellows, on the right-hand side. Based on initial tests, we have constrained the flux density to a minimum of 250 millitesla in the on state and a maximum of 50 millitesla in the off state. Hallback mechanisms that do not comply to these constraints are represented by transparent data points and are excluded from our investigation. A rising trend is observed at increasing numbers of square segments, with a drop at large area fractions and at starting from a large number of square segments, more specifically 24. There we can see a drop. And as well as for the internal grasp diameter, increasing the relative magnetic permeability of the MR fluid will also improve the performance of the Hallback mechanisms, but while increasing the internal grasp diameter will deteriorate the performance. Then, based on the multi-objective graphs, certain design guidelines are drawn. First, a magnetic dipole is prevalent over a magnetic quadrupole because of its lower mean magnetic flux density in the off state and the higher homogeneity of the magnetic field in the on state. Second, equally sized area fractions for the inner and outer cylinder are crucial to get an optimal field compensation in the off state. Third, the total area fraction of both cylinders need to range between 0.5 and 1. This is a trade-off between a sufficiently powerful Hallback mechanism and a limited amount of magnetic material, which is of an economic relevance. Then, as already mentioned, square magnet shapes are preferred over annular shapes because of its standard purchasable shape for the square magnets and the increased manufacturing costs for the annular segments. Then 5, a number of 16 magnet segments are needed. As we could see in the figures, the drop was at that point, and it's a trade-off between a compact Hallback mechanism that can sufficiently stiffen the MR fluid inside the radial bellows. Then the relative magnetic permeability of the MR fluid is set to a mean value of 2.5, which is common in literature, as well as for ferrofluids. Increasing this quantity is dominated by the chemical composition of the fluid and will at his turn adversely affect the gravitational sedimentation stability of the fluid. Then next, a non-ferromagnetic gauge material is preferred, so it increases the affinity of the magnetic field lines to close through the more magnetically permeable MR fluid instead of the gauge material. And then finally, ferromagnetic objects could provide a more stable grasp due to the attraction forces of the magnetic field, the applied magnetic field. So, and then based on these design guidelines, the most optimal Hallback mechanism for our robotic gripper application is proposed, of which its geometrical and magnetic properties are listed. This mechanism possesses a multi-objective value of 0.65 and yields mean magnetic flux densities that easily meet our flux constraints of a minimum of 250 millitesla in the on state and a maximum of 50 millitesla in the off state. The figure below shows a 2D field map in both operational states. More red means a higher flux density, blue means a low flux density. And then finally, future work aims at expanding the search space to allow to alter the number of magnets, the individual magnet sizes, and the individual magnet orientations for each cylinder individually. By implementing an informed search technique, such as a Bayesian hyperparameter optimization, the whole optimization process could be made in a more automated fashion without the user intervention. These techniques use the multi-objective value of previous runs to propose new promising parameter sets to explore in the future. And then finally, 3D simulations, instead of our 2D magnetostatic simulations, could cope with a finite cylinder length and with the adverse side effects of field distortions at the end faces of the cylinders. So, and with these references, I will end my presentation and would like to thank you for your attention. If there are any questions, I would be happy to answer them. Yes. 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 Okay. So you mean that the radial bellows can only contract to a specific diameter, if I am correct? Is that what you mean? So it's designed for axial objects. That's the constraint for this design, and it can only contract between 10 millimeters. 10 millimeters and 58 millimeters, and it's according to a commercial variant of Zimmer, the Zimmer RG 1060. And so that's the constraint. We have made our design according to that commercial variant, and of course, in the future, maybe smaller variations could be made, and so smaller designs. For instance, Zimmer also provides a smaller radial bellow gripper, but the commercially available grippers are inflated with air, and our MR-based gripper could improve the pull and bending stiffness of the radial bellows in a vertical and in a horizontal object position, respectively. So that's the benefit of our design, but it's dimensioned, it's intended for actual objects. So, for instance, transmission shafts. Yes? Yes? Okay, so the question is first. One of your questions was what is the time to change the aggregation state, and as can be seen in the video, the reaction time of the MR fluid is in milliseconds. But to inflate the radial bellows, that was also one of your concerns. Dus the reaction time of the radial bellows, that is that's up to the fluid pump system. So the how fast can the fluid be pumped into the radial bellows, and that's also part of its viscosity. So there needs to be a trade-off. So MR fluids with a low viscosity can be easily pumped. So the reaction time is very fast, but the sedimentation stability, as I have mentioned in one of my slides, the gravitational sedimentation stability of the MR fluid will drop at low viscosities of the carrier medium. So we need to make a trade-off. A higher viscosity of the carrier medium would mean a more stable MR fluid, but a slower reaction time, so a slower grasp. Yes?
that quite slow, or don't we lose that advantage by using another transmission? And aren't there other transmission that we could think of to quickly turn?
Yes. Okay, so your question is whether or not this worm drive is a slow mechanism to provide a relative angular rotation between both cylinders. Yes, that could be true. So this is just for the prototype. So this is just for the prototype that we have implemented a worm drive to switch the magnetic field on and off. So maybe there are other actuation mechanisms, for instance with a pneumatic, pneumatic of a hydraulic system. That could be possible. That if we want to commercialize this design, we definitely need to look further into that. But one of the other advantages of a worm drive is that like I said, the stiffness of the MR fluid can be adjusted, can be continuously adjusted between a minimum and a maximum, as could be seen on the figures of the Halbach mechanisms working principle on these figures. So the magnetic field inside the Halbach cylinder's core can be continuously regulated between a maximum and a minimum value. So it could be interesting to also, with a worm drive, we can exactly rotate the Halbach mechanism for a certain degree. So we can stiffen the MR fluid continuously. So for a certain application, it's maybe more useful to not only switch the gripper between on and off, but regulate it continuously. Yes? Okay, so your question is whether or not the maximum values of the dipole configuration and the quadrupole configuration are the same. And there's a simple answer, it's not. So it's just for this image, but the maximum values are not the same. It's the value of the magnetic flux density inside the core. It depends on a lot of parameters, and they are shown on this slide 13. So all these parameters, the magnetic field depends on all these parameters. So it's not easily said that that the maximum value of a dipole is the same as a quadrupole is not. So it's it's a multi-objective problem. Yes?
Next time you should start with that. Can you just give one or two examples where is the benefit and the potential application of your proposed gripper to the commercial variant, for example?
So the question is, what is the benefit of our gripper design, the cylindrical radial bellow gripper filled with MR fluid instead of compressed air. And this the MR fluid could improve the pull and bending stiffness of the radial bellows in a vertical and horizontal object position. So that is the main benefit. In compressed air variant, the radial bellows could function as a cushion, but with the MR fluid, it's a stiff structure. So the axial object, for instance, the transmission shaft, is much stiffer. It's a secure grasp compared to the compressed air, and definitely at manipulating So for a robotic application, when we manipulate objects at a high acceleration, this could be a benefit. The increased pull and bending stiffness.
You can make a link with the potential clamping.
Okay, so another application of this this principle is not, it's more or less gripping, but we see it as another application. It's clamping. So we can use it. This device we could mount it in a table and in a work table to clamp work pieces that can be manufactured. So there can be in CNC applications. This principle could be used as a clamping system. And so even on a robot, yes. Thank you.
ik hier binnen kan, gaan heel veel mannen binnen.
paswoord staat hier.
Ik ga mijn presentatie opzetten. Nee, het was heel hectisch om alles gedaan te krijgen.
Komt allemaal goed.
Ik moet om 1 uur denk ik, ben ik de eerste in de namiddag?
Jij bent de eerste.
Spannend. Ja. Er is nog een poortje. Ja, nu heb ik dat alles. Want ik had het normaal een Google Slides. Dat ik dan na kan doen.
Lijkt ook wel een hele lekker.
Ja, uiteraard is het nou een beetje gedaan. Ik zie het niet meer. Oké, super. Ik ga dat gewoon zo klaar laten staan.
Jawel, maar ik heb hem moeten aanpassen omdat de filmpjes niet werken. Dat is goed. En daar hebben we nu toch nog wel 7 minuutjes voor.
Ja, mag iets meer licht aan, want dat is zo lichtsterk om in slaap te vallen.
Oh, maar dat is te fel.
Dat is een beetje te fel.
En dit is de les, de lesinstelling. En dit is de presentatie. Dus dat is de bovenste.
Want de lesinstelling vind ik ook goed.
Ja?
Alleen hiervan voor, kun je die apart uitzetten?
Wacht hè.
Want anders krijg je heel veel licht op de presentaties op. Dat heeft dus maar 1 USB-poort, nee 2. En die zijn alle 2 bezet. Enig idee welke ik mag uittrekken, iemand? Nee. Ja, nee, maar jij was met link bezig, dus dat was ook goed voor mij. Maar de vraag is, er staat mijn presentatie op, welke ik mag uittrekken?
Dat van die muis.
Ah, dat is van de muis.
Ah nee, dat weet ik niet wat dat is.
Ah ja, uiteindelijk.
Oh, black screen.
Hoe dan?
Nee, maar het is in orde, denk ik. Dus de lampen voor mijn bord zijn uit. Dus nu zo is het goed.
Dat is zo'n beetje zeker wat allemaal.
Je herkent die precies niet, om. Zeg je... Rafael. Ah jawel, sorry, ik heb niks gezegd. Ik heb niks gezegd, ik heb niks gezegd. Wat? Aderen? Wat is dat? Is daar een specifieke map voor aangemaakt? Nee.
Dat stond er precies door.
Nee.
Ja, oei, wie heeft dat dicht gedaan?
Ik denk niet.
Ja, bij download. Kijk eens bij.
Is dat deze? Nee,
Nee,
deze
wacht.
stond open.
Maar Charlotte. Wacht, die gaat stond bij Chrome. Ik denk. En dan. Wacht nee, ik denk dat ook gedownload.
Wacht, dat gaat hier. Wacht, dat gaat
Kijk
in
eens bij
dezelfde
down-
staat.
ja, ja.
Weer hier.
Dat staat waarschijnlijk die downloads map.
Ja.
En
Deze
dan,
is dat, hè?
van boven.
Nee, Ctrl
Ah,
V.
wat staat er tussen?
Voilà. V2 staat er. Ja, V2 hè, hoop ik. En anders dan is het zo hè. Die mag ik sluiten hè. Ja. Moet dat? Nee, moet dat?
Dat is niet, dat is niet verplicht, maar dat is toch aangeraden.
Ah, nee. Wat staat er in vergelijking?
Van kabouter was, niet dat?
Ah ja, man. Wauw.
Dat is niet verplicht, dat is slechts een aanbeveling.
Ja, het is echt heel raar.
Hè?
Ja, ik heb dan gewoon een PowerPoint gedownload.
Ah, oké. Hopelijk is het nu de juiste versie. Ja, ja. Dat is waarschijnlijk goed gekregen.
Ja.
Oh, moet je een micro?
Ja, of een headset, want anders er is een livestream. En anders dan horen ze niet aan de andere kant. Ik weet niet hoe je het liefste doet.
Ik zal de micro gewoon.
Ja?
Hallo? Oh. Dank je. Ja, liefst. Mijn presentatie wordt opgenomen, hè?
Alles normaal gezien.
Ja, maar die is achteraf nog beschikbaar, bedoel ik. Ja. Ja.
Dank je. Het is toch de bedoeling dat hij komt, hè? Of, ja. Voor 12 uur 's nachts toch? Ja, ik denk, ja, kijk eens. Echt? Ik vrees er voor 3 of 4 zou al veel zijn. Oh, 5 toch? Of Gert met 5 tabbladen. Ja, ik denk dat hem daar is. Okay. So, hello everyone. My name is Stijn Schildermans, as most of you probably know, and I will present my PhD project to you, which is titled Elevating Multithreading Further into the Cloud. First, let's start with an introduction and some background information. The main motivation for my PhD project is the fact that during the past decade, cloud computing has emerged as a very popular software deployment platform. And cloud computing basically means that instead of hosting your applications on your own infrastructure that you manage yourself, you actually upload it to some remote platform which is managed by an external cloud provider. And this cloud provider will just send you a bill every month based on the exact amount of resources that you consumed. Now, the cornerstone of cloud computing is a technology called virtualization. And this the idea behind this technology is that you basically separate the notion of the operating environment from the physical hardware supporting that environment. So here on the slide you can see a traditional software deployment method, basically a system stack. So you just have your physical hardware, and on that hardware you have an operating system, or in technical terms a kernel, and within that operating system you host your applications. Now, with virtualization, you actually introduce an extra layer of abstraction between the hardware and this operating system, which we call the hypervisor. And the hypervisor is basically responsible, or it allows you to host different, distinct operating systems on your physical system. So you can have multiple separate operating environments on one server, basically. Now, there is a bit of a problem with this idea or this virtualization technique, and that is, of course, that operating systems are traditionally not designed to be run in such an environment. So each operating system or each guest kernel assumes to be in full control of the hardware, which obviously it isn't in a virtualized setting. And there are several techniques that have been developed to mitigate this problem. And the most popular technique used today is what we call hardware-assisted virtualization. And how this works is actually that in the CPU itself, in the physical hardware, there are several extensions that have been implemented that constantly monitor your virtual machine. And whenever one of the guest operating systems tries to perform an operation which is not allowed to perform in a virtualized environment, the hardware will trigger a kind of exception, which we call a VM exit, and it will pass control to the hypervisor software, which will then emulate the illegal operation, let's say, and after that it will pass control back to the virtual machine. So now I've explained to you the basics about virtualization. Now let's look at the other important part of my PhD, which is multithreading. Multithreading, most of you are probably familiar with that, and it simply entails splitting an application into multiple parallel execution streams within the same virtual memory space. Now, the problem with multithreading in a virtualized environment is that by their nature, multithreaded applications tend to perform a lot of operations that have to be intercepted by the hypervisor. So a lot of illegal operations, let's say, in a virtualized environment. And these illegal operations, they lead to a large amount of various performance penalties. And the total sum of all these performance penalties is what we call virtualization overhead. So let's take a look at this virtualization overhead for multi-threaded applications. And what we did is basically we executed a large amount of applications, a benchmark suite in a virtualized environment. And here you can see the results of basically the virtualization overhead that we collected for all those applications. And as you can see, it is not easy at all to see some kind of pattern between the applications. There's a lot of variation between individual benchmarks. So that implies basically that virtualization overhead is has many different sources, and all these sources interact in a unique way depending on the applications. So the best way to understand this this graph is to try and group benchmarks that have similar overhead patterns and try and break down this overhead based on this grouping. So we actually identified 4 different groups. The first of which is a group of benchmarks which have negligible overhead, like these. And of course, we don't need to discuss them. But the second group is quite interesting, which are benchmarks which show a large amount of guest level virtualization overhead. And by guest level virtualization overhead, we mean operations that take a lot longer in a virtualized environment than they would in a bare metal environment without actually requiring intervention from the hypervisor. So these applications do not generate VM exits, but still they are a lot slower in a virtualized environment. We found that the principal cause of this guest level virtualization overhead is what we call NUMA abstraction. And to understand this, of course, you need to understand what NUMA is. And NUMA stands for non-uniform memory access. And that's actually, it simply means that you can have a server which has 2 distinct CPU sockets. And each of those CPU sockets has its own memory bank. And all of the CPUs can, of course, access all of the memory in the system. But if this CPU here wants to access memory on another NUMA node, that will be a lot slower than just directly accessing memory on its local node. And in a bare metal environment, operating systems solve this by taking the NUMA architecture of the system into account and scheduling applications so that the memory latency is minimized. The problem in a virtualized environment is that the hypervisor will actually abstract this underlying NUMA architecture. So the virtual machine in this example, instead of seeing 2 NUMA nodes with each 2 virtual CPUs, it will just see 1 NUMA node with 4 CPUs. So the guest operating system cannot optimize its scheduling behavior, which can lead to severe virtualization overhead. Now, several solutions already exist to kind of mitigate this issue as best as possible. And we evaluated these methods. The first one is quite simple. We just expose the NUMA architecture of the system to the virtual machine, which actually solves the performance problems very well. But the problem there is that you take away a lot of the flexibility advantages that virtualization brings in the first place, because now you have to you can only schedule virtual CPUs on the specific NUMA node where they belong, or where they, how you communicated it to the guest operating system. The other approach is using an automated NUMA manager, which is just a small program which runs on the host machine and constantly informs the hypervisor about the memory latency in each virtual machine, so that the hypervisor can then schedule virtual CPUs so that this latency is minimized. This, of course, mitigates the flexibility drawback of exposing NUMA architecture, but it can be quite costly. This NUMA manager can take up a lot of CPU resources itself, so it sometimes isn't very efficient. So right now, there is no universally satisfying solution to this problem. A second group of benchmarks, or a second form of virtualization overhead that we identified is host-level virtualization overhead. So this is overhead purely induced by VM exits and processing these VM exits. And the first major cause of this overhead for multi-threaded applications is actually blocking synchronization. Blocking synchronization may be familiar to some of you as well, and that basically means that in every application there are some areas of code which we need to execute sequentially, so only one thread can access that code at the same time. And to protect these areas, what they do is they create something called a mutex lock, which is a data structure that has to be claimed or locked by one thread. And once one thread has claimed this lock, then any other thread, so for example the thread here on the right, that tries to claim the lock will actually go into a blocking state. So it will yield its resources to the operating system, and the operating system can do something else with those resources, or most likely it will just send the CPU into an idle state, so nothing is done at all. And the thread will just, the blocking thread just waits until the original thread on the left here releases the lock, and when that happens, most likely an interrupt is sent, a special kind of interrupt. We call it a scheduling interprocessor interrupt. And that wakes up the CPU that just went to sleep and then schedules the new thread, and so execution can continue in that way. So in a bare metal environment, in native environment, this is all really nice and efficient, but the problem is in a virtualized environment that you actually induce 4 different VM exits in this cycle of locking and unlocking the mutex lock. The first one happens when this second thread here tries to claim the lock and it has to block, then it will actually disable what is called its scheduler tick. And a scheduler tick is a periodic interrupt that every CPU just has on the background. It's a kind of operating system background task that is always running, and that has to be disabled when the CPU enters an idle state. But this step induces a VM exit. Then entering the idle state itself induces a second VM exit. So that's on the blocking side. And then when the block thread has to be woken up again in this step, you have 2 more VM exits, one for the interprocessor interrupt to wake it up, and a second one to enable the scheduler tick again. So, of course, this induces a lot of virtualization overhead, as I also already said, and that brings us to the first major contribution of my PhD project, which we called Paratick. And Paratick is simply a method to get rid of those 2 VM exits, so the disabling and the enabling tick VM exits. So what we did is, instead of letting the guest operating system manage this background task, this scheduling tick, we simply let the hypervisor manage that scheduling tick. And the guest, we just removed all the scheduling tick programming code from the guest operating system. We implemented that in the hypervisor, and the guest will simply wait for the hypervisor to inject the tick whenever it's needed. So that's the basic principle behind Paratick. And by doing this, we could improve throughput for multi-threaded applications by 15% and reduce their execution time by 2%. And an interesting side effect of this technique was that it also is very beneficial to I/O-heavy applications, because I/O-heavy applications have to cycle through this blocking and unblocking states by their nature a lot as well. All right, so the second major source of host-level virtualization overhead, which is unrelated to what I told just a second ago, is what we call TLB shootdowns. And TLB shootdowns are caused by sharing memory between different CPUs. So right here you see the blueprint of a CPU again, and you know that every CPU has a number of caches, and one of those caches is called the TLB. And the TLB is used specifically to store page table entries. And page table entries, again, are mappings from virtual memory addresses to physical memory addresses, which is a technical term basically for, it's used for memory accesses. Let's just keep it at that. And the problem is, whenever one CPU needs to changes something to this memory address mapping, it needs to communicate that to all the other CPUs. And that's done through interprocessor interrupts. And the sum of all these interprocessor interrupts is what we call a TLB shootdown. But, as we already saw a few slides ago, these interprocessor interrupts all cause VM exits, again leading to a lot of virtualization overhead. So, specifically for multi-threaded applications which have a kind of like a sinusoidal memory allocation pattern, this can be a big problem. Because when a single thread releases some memory to the operating system, then a TLB shootdown is sent because the heap is resized for that thread. But a few seconds later or a few milliseconds later, it will maybe claim some new memory, and then it goes through the cycle again. And the problem with highly multi-threaded applications is that a single thread usually doesn't impact the memory usage of the entire application at all. So if you have one thread that frees 50% of its memory, but you have 1,000 threads in your application, then that 50% really doesn't matter. And the way that memory allocators are built is that they usually, each thread is viewed as a distinct entity. So threads don't know about each other's memory usage. And that is what causes a lot of this overhead, these TLB shootdowns. And that leads us to the second major contribution of my PhD, which is called PTLB malloc 2. And that project simply consisted of like kind of bridging this barrier between individual threads. So instead of looking at the memory usage of an individual thread, we looked at the memory usage of the entire application, and only when that memory usage fluctuates a lot, only then do we release memory back to the system. So we take a number of parameters into account to do that, and that concept is what we call global hysteresis. And by implementing that idea, we got another performance gain of about 3% on average. Then the final form of virtualization overhead I want to talk to you about is what we call overcommitment overhead. And that is virtualization overhead that only occurs when you have multiple virtual machines sharing the same physical hardware resources. The main form of overhead that occurs in this scenario is what we call user-level spinning. And user-level spinning basically happens when you have a construct similar to what you see on the slide. Basically, when someone implements a spin lock-like structure in his own application. So you just, in a while loop, you just constantly check a variable. If the variable becomes 0 or 1 or whatever, you change the value of the variable, and that's a way to serialize execution very easily. The problem is, in an overcommitted virtual environment, it's possible that a CPU that holds a spin lock like that can get descheduled by the hypervisor, so that the hypervisor can schedule a vCPU from another VM. And when that happens, all the other vCPUs from the first VM will start spinning for a very long time, waiting for this descheduled CPU to finally be rescheduled and be able to release the lock. And that actually introduces a very large amount of virtualization overhead. Many different solutions could be used to address this, but none of them are really satisfying yet. They all have a lot of downsides that we can't get around right now. So this is really still a big open question how to address this. So if any of you feels ambitious, please let me know. Then finally, I want to conclude my presentation by giving you guys some advice about what you can do with all of this to develop your applications in a way that minimizes virtualization overhead. Here you can see a few points to take into account. You should try to minimize main memory accesses to minimize the NUMA locality issue. So you can do that by making sure you allocate memory or you access memory that's located in caches. You can focus on data parallelism to minimize thread interdependencies. You can use coarser memory allocations to minimize TLB shootdowns and also release that memory as quickly as possible so that other application threads can use the newly released memory to make sure that it doesn't get returned to the operating system. And finally, and most importantly, do not ever use custom spinning synchronization primitives when you're planning to run your application in a virtualized setting. To prove or to provide some evidence of the efficacy of this, we applied these guidelines to a single benchmark from the list that I showed you before. And for that benchmark, we were able to improve performance by 40% just by using these guidelines at application level. So in conclusion, virtualization overhead can still be problematic for a lot of multi-thread applications. But the good news is that a lot of advancements have been made in the past 10 years. So it used to be the case that sometimes applications were slowed down by a factor of 5 or more. So these days that has been reduced by a factor of maximum 2. This PhD project did 3 contributions to further reduce virtualization overhead for these multi-thread applications. And all of these are located at a different level in the system stack, let's say. At pure system level, we had Paratic, which has a 2% improvement. At runtime level, PTLB malloc 2 with a 3% improvement. And at application level, of course, for the application we tested, we got 40%, but it's heavily dependent on the specific application that you use. So you can expect anywhere between a few percent to maybe 40–50%. So while multi-threading related virtualization overhead is still significant, emerging techniques and careful application design may largely mitigate it. Thank you for your attention, and if there are any questions. Yes? Yes. So, okay. So the question was that I mentioned performance gains of 2 or 3%, but what is that performance gain relative to? And it's relative to the standard state-of-the-art techniques. So. Yes? It's separate. It's completely separate. So if you add everything together, you will get around 45–50% maybe. Mhm.
it would be nice, I think, to also give some example snippets of code to illustrate good and bad practices.
Mhm.
But of course, you didn't have a lot of time to explain.
Mhm,
It would
mhm.
be nice to see some
Yes. Yeah, I will definitely add that to my thesis. So you're invited to ask a copy. All right. Thank you. Yes. Oh, okay.
Thank you for the talk. Stan, can you discuss threats to validity of your research?
All right. All right. So the question is, can I discuss threats to validity for my research results? And that is most important, I think, for the first part of my research, like the slide I showed with all the benchmarks. Basically, the main threat to validity always with experiments like this is that we have to take a specific subset of workloads to evaluate. And of course, I categorized the applications. I made this 4 categories, but it's always possible that some other specific workload has another form of virtualization overhead that we couldn't identify because we didn't evaluate a workload like that. But we chose the benchmarks. The benchmarks that we chose was actually Parsec benchmark suites, which has been developed and used in a research context for a decade or so. And so we cover a wide range of applications, as wide as possible. The second major threat, of course, is that we gathered results for a lot of system settings, but of course the exact quantity of virtualization overhead will vary greatly depending on your system. So if you try a different system, then you will get different numbers. But the underlying causes behind this overhead will remain constant for all systems. So the exact data may differ, but the causes are the same. Mm-hmm. Oh, okay. Okay, thank you.
Hello everyone, my name is Martijn Kramer and I'm a doctoral researcher at the Department of Mechanical Engineering of KU Leuven. In today's talk I would like to present my latest work on a probabilistic decision model for adaptive task planning in human-robot collaborative assembly, and that based on designer and operator intents. But before we start off, I would like to thank my colleague from Campus Diepenbeek for organizing this PhD seminar. On today's workflow, we see more often humans and robots operating on a common product without physical barriers. However, human operators are still often regarded as intelligent manipulators whose tasks can be planned beforehand. This is often referred to as human-robot cooperation. We suggest that to achieve a more natural collaboration, the robot should act more adaptively by considering the intentions of both the designer and operator in its decision-making. The operator intent is defined as the operator's preferred sequence for assembling the product, which could be, for instance, one of the 3 sequences pictured on the slide. This 6-part ballpoint pen was firstly described by the French scientist Bourgeot and will be used as an example use case throughout this presentation. The designer intent, on the other hand, is the knowledge about the assembly product and process that was incorporated in the design. This could include information about the geometric information of the different components, how these different components fit together, what their material properties are, etc. Based on this data, we could infer possible assembly plans and even unfavorable tasks to humans or robots, based, for example, on the part's weight or its flexibility. Since the early 90s, and/or graphs have been used to compactly represent assembly plans. Formally, they can be described as a directed hypergraph whose vertices represent the feasible subassemblies, as shown on the right-hand side for the ballpoint pen. As the name of the graph suggests, these vertices relate in two different ways, and relationships represent the composition of multiple child subassemblies into one single parent subassembly, and are denoted by dashed lines connected by an arc. Some hyperarcs are simplified for conciseness and therefore drawn as solid lines. Or relationships, on the other hand, represent the different ways in which the same subassembly can be shaped and are represented by multiple hyperarcs originating from the same vertex. In this research, the reverse cut set algorithm was used to automatically construct the and/or graph. For this, we used the geometric information and spatial relationships from the CAD data of the product, for which we have developed a workbench in the open source CAD software FreeCAD. During the generation of the and/or graph, feasible subassemblies are checked against topological, geometrical, and technical constraints in order to guarantee their practical manufacturability. Next, this and/or graph is translated into the assembly state graph, which can formally be described as a directed acyclic graph. Its vertices represent the different assembly states, and an assembly state is modeled as the different components, the individual components or subassemblies that have been created till that moment by either the robot or operator or all together. So the vertices of the assembly state graph represent the different possible assembly states, and its edges represent the different assembly operations connecting these assembly states. The assembly state graph starts in the initial state, which consists of the individual disjoint components, and ends into the final goal state, which consists of the completed product. As mentioned before, the operator intent is the operator's preferred sequence for assembling the product. This graphically translates into the various paths through the assembly state graph, starting from the current assembly state and ending in the final goal state. The two color paths on the right-hand side pictures two possible operator intentions. This intention graph results from the assembly state graph, the previously discussed assembly state graph, and can also be formally described as a directed acyclic graph. The figure on the right-hand side, the bottom right, shows the intention graph, and the vertices that correspond to the color paths in the assembly state graph are drawn in matching colors for clarity. The vertices of the intention graph relate to the set of possible operator intentions, which relate to the sequences of assembly states in the assembly state graph. And the edges represent the different assembly operations which cause transitions between these intentions. But before addressing our decision model, let's introduce our use case to evaluate its performance. The right figure pictures a top-down view of our setup. On the left side you can see our storage that is equipped with all the necessary assembly components and tools. And the human operator and robot are instructed to jointly assemble the 6-part product by acting one after the other, so sequentially. Since in industry the entire assembly of a product is often divided over several workstations, we are convinced that this 6-part ballpoint pen is representative for a typical product that could be assembled by a single operator in industry. And initially, the robot was impersonated by a second person. This allowed us to first focus on the design and performance of the decision model rather than having to deal with motion or grasp planning. A Kinect camera was used for recognizing the operator actions by registering the different assembly components and tools picked from storage when performing an assembly operation by the operator. All objects in the storage covers a unique Aruko marker, which becomes visible when a part or tool is picked from the storage by one of the agents. And when the tool's marker is detected, all visible markers are recorded and sent to the decision model. The robot operating system is used for interfacing the camera and detecting the Aruko markers, and for coordinating the communication between the vision system, the robot, and the decision model. An action client and server framework was set up in ROS. Since the operator intent is part of the mental state, is not directly observable through sensing or perception, we therefore modeled the operator intent as a hidden variable in a partially observable Markov decision process, or POMDP. A POMDP allows to probabilistically plan robot actions in the presence of uncertainty by maximizing the expected sum of future rewards. And the resulting robot policy defines the best action to perform by the robot under a given belief of operator intentions, or in other words, a probability distribution over operator intentions. The POMDP designed in this work is formally described by a 7th tuple, of which the right figure pictures some of its variables and their conditional dependencies. The first variable of a POMDP is its state space, which consists of the collection of all operator intentions. And graphically, this relates to the set of vertices of the previously described intention graph. The second variable is the robot's action space, which consists of all actions that a robot is capable of executing, extended with a wait action. And for the ballpoint pen, this corresponds to the hyperarcs of the previously described AND/OR graph. The state transition function models how the operator intent changes in response to robot actions. Suppose that the world is currently in intention I, so the operator has intention I subscript T, and the robot performs action A, highlighted here on the slide in green. This will cause the assembly state to change as well as the operator intent. And this is the result of our intention representation, which is a combined representation of both the current assembly state and the operator's desired path through the assembly state graph. So when the assembly state changes, the operator intent will change as well. So now that the world is currently in this intermediate intention I subscript T plus 0.5, it's the operator's turn to assemble. He or she can decide to wait, therewith remaining in the same state, which is pictured on the left-hand side, or the operator can decide to act, therewith transitioning to a successor intention, which is shown on the right-hand side. Since we don't know the operator's choice beforehand, chances are distributed uniformly over both options. As mentioned before, the true operator intent has to be estimated from noisy observations, since the state of a POMDP is hidden. And these observations consist of the set of assembly components and tools picked from storage when performing an assembly operation. Now, given the current intention I subscript T of the operator and the action previously performed by the robot highlighted in green, the observation function specifies the probabilities of observing each of the different operator actions under this intention and action performed by the robot. First, all intentions that precede the current operator intent I subscript T, highlighted in orange on the bottom side of the slide, are listed. Next, all intermediate intentions, which are the result of the action performed by the robot, are filtered out. And finally, all observations which relate to the actions that the operator could have performed under these intermediate intentions and that cause a transition from the intermediate intention to the current intention I subscript T, are grouped together. since the operator could have performed any of these actions and observations, chances are distributed uniformly over this set of of observations. And moreover, an additional small probability is assigned to the blank observation in case that the action was performed correctly by the operator, but that this action was unnoticed by our vision system. The reward function determines the immediate reward that the robot will get when performing an action under an operator intention. For this, we have divided the entire set of operator actions into two subsets. The desired robot actions are the actions that correspond to the directed edges pointing outwards from the corresponding vertex in the intention graph. And the second group of robot actions are the actions that are unfavorable to humans, including non-ergonomic, dangerous, or repetitive actions. Now, if the robot performs an action that is aligned with the operator intent, so it belongs to the category of desired robot actions. And it's an action that is unfavorable to the human operator. The robot will receive the highest positive reward depending on whether this action is also part of the set of unfavorable actions as pictured on the top right side of the slide. Dus if this action is not part of the set of unfavorable actions to humans, the robot will get a slight negative reward of -2. This will encourage the robot to take on actions that are aligned with the operator intent and actions that are harmful to humans. Then if the robot performs an operator which isn't aligned with the operator intent or which doesn't match the operator intent, it will get the highest negative punishment of -50. And at any time, waiting is tolerated, for which the robot won't receive any reward, which is pictured on the left-hand side. And these reward values are determined empirically. And finally, the discount factor, the last variable. The discount factor determines to what extent immediate rewards are favored over future ones. And this variable can take on a real number value between 0 and 1, 1 not including. And we have set the discount factor to a value of 0.9. And then let's see how this decision model performs in a real experiment. So at first, the robot has no information about the operator intent, so it decides to wait and take some observations. And then after the third time step, the robot is sure about the sequence that the operator is trying to follow, and it starts participating in the assembly sequence. So from this moment on, the robot will start participating. The POMDB generated in this work is characterized by 69 operator intentions, 23 different assembly actions, and 12 different observations. To compute the robot policy, the point-based SARSOP algorithm from the ABPL toolkit was selected. After 1,000 trials, an approximate alpha vector policy was found offline in about 131 seconds, which consists of 382 alpha vectors. And as a side note, the total time required for constructing the previously discussed graphs together with the decision model amounts to approximately 1 second, which makes up only a fraction of the total time required for solving the POMDB. And in order to investigate the robot's adaptability to the operator intent, the operator was asked to perform 3 different assembly sequences or to follow 3 different assembly sequences each trial. The subplots of the bottom right figure each relate to a different assembly sequence, of which the horizontal rows shows the probability distributions over the possible operator intentions. the darker the cell's color, the more probable the operator intent is. And the vertical axis represents time. And then the evolution of the true operator intent is denoted by the colored lines and paths in the intention graph on the top, and the colored paths or lines in the figure on the bottom. And these are drawn matching colors, again for clarity. For the first two experiments, it was observed that the system was able to correctly estimate the operator intent after two time steps, or since after two time steps. This is shown by the unimodal probability distribution over operator intentions from time step 2 onwards. For the third experiment, the same observation is made, but after time step 4. And due to our reward function, after these points in time, the robot is sure about the sequence that the operator is trying to follow, and the robots are participating in the assembly case. And a supportive video of the conducted experiments can be found on the YouTube channel of our research group, ACRO. So in this presentation, we have demonstrated that a probabilistic decision model could be or can be constructed from the CAD model of a 6-part product, and that this model is able to estimate the operator intent by registering or recognizing the operator actions for three different assembly scenarios. In addition, the scalability of our approach to a more industrial product, in this case an 11-part pneumatic cylinder, was examined. The table on the bottom right shows that as the connectivity between the components of the assembly increases, or in other words, the number of feasible subassemblies, the number of actions and intentions drastically grows. And these larger action and state spaces will significantly extend the time required for solving the POM-DP. So that is a challenge we have to overcome. So future work will try to deal with these challenges when scaling up to more complex assemblies. Currently, the assembly happened also sequentially. So the operator and the robot performed an assembly action one after the other. But in order to increase the productivity and increase the system's acceptance by industry, future work will focus on enabling these parallel assembly actions. Furthermore, a user study is foreseen involving participants of different ages and levels of expertise, in which their experiences will be subjected to a qualitative analysis. And finally, future work will involve validating our approach on a real robotic manipulator or with a real robotic manipulator, such as Universal Robots UR5 and Archive Human Interface Mate as the industrial vision system. And this brings us to the end of this presentation. I would like to thank you for your attention, and if there are any questions, I would be happy to answer them. Thank you. So the question is about other techniques to deal with these parallel assembly actions, or to enable these parallel assembly actions. So that was on this slide. There are actually two options we foresee. The first option is refactoring or state representation. So if the robot and operator are performing assembly actions in parallel, it's important that the robot is aware of the assembly operation of the operator in order to prevent that the robot will perform the same operation as the operator. So if you want the robot to account for the assembly operation of the operator, or the action of the operator, we have to incorporate the assembly action of the operator into our state representation for the POM-DP, which isn't there at the moment. So the first option is refactoring or state representation for the POMDP and see if that will work. Another option was currently pointed out by one of my supervisors from my doctoral committee, and it is the use of BatteryNet as another technique for representing the assembly state. And there is a question on slide 6. So the question is about whether, of why there is only one arrow pointing outwards from the blue dot in the intention graph, while we would say that there are actually two paths originating from the blue rectangular shape in the solid rectangular shape. From that state there are actually two paths. What's the reason why there's only one arrow pointing outwards from the blue dot in the intention graph? That's due to an assumption that I made. So I made the assumption that when the operator has a certain assembly sequence in mind, such as the blue path, it will follow that sequence. Thus it will stay, or it will not completely change its intention. So if we say that there is an arrow pointing from the blue dot towards the path, the upwards path through the assembly state graph, that would imply that the operator would completely change its sequence. It's the sequence he's trying to follow. It's an assumption that I made. So from the blue dot, there is only one intention, or there follows only one intention from the blue dot, and that is the path that starts from, I hope that everyone can see this, that starts from the assembly state, the assembly state that follows on the current blue assembly state. The human can, we don't make an assumption about which intention the operator has, but the only assumption that we made was that when the operator has a certain path in mind, it will most likely follow that path when assembling or completing the product. It will not, in the middle of the assembly, change the path that he is trying to follow, he or she is trying to follow. But it's something that we can look at in the future to improve the framework. That's So you are suggesting to include undo actions, so that the operator or robot can regress in the assembly state graph, thus undo a certain assembly action. That's a good remark. That's something that we are envisioned for the future. Because currently undo actions are not allowed by either the robot or the operator. Only progressing in the assembly state graph is currently considered. But that's something that we can include for the future. So the question is about whether, or the questioner noticed that the robot was, or was starting to act after only, or after the third, or the third time step. And so the questioner suggests if we can learn from this, if we can transfer this intention estimation to the next trial. And yeah, indeed, this I was thinking about. In the first time step, the robot is still hesitating in participating with the human operator, but from the moment that he correctly estimated the operator intent, it can use that information for the next trials to start collaborating from the first moment. And also, this, the fact that the robot is hesitating, or that the robot only starts acting after the third time step, is due to our reward function. Dus in our reward function, we specified a quite large punishment for doing actions that doesn't match the operator intent. It was a punishment of -50. But I have observed that when we alter this punishment, this value, we can control the eagerness of the robot to act. So if we lower this value or increase this value as you wish, so if we make it less negative, we can increase or improve the eagerness of the robot, so that it will start participating early on in the assembly experiment, although with the risk that the robot performs an action that doesn't match the operator intent. So it requires mutual adaptation from both the operator and the robot, if we go for this. Yes? So the question is, if we consider the case, or the case that if the operator picks an object from the storage and don't use it, what would happen then? Is the intent correctly estimated or not? And for the moment, we didn't take that into account. So this, when the operator picks an object from the storage, we assume that he will use it for assembly, and not that he will set it apart or put it apart. So the question is about if we could learn or gather more information from the trajectory of the parts that are manipulated by the operator for making or improving the intention estimation, and how hard it would be. Yeah, that's a good question. I have to think about it, how we can incorporate it in our POMDP. I think that it would be possible to do something like that. But yeah, definitely, if we could use the trajectory or the pose of the different objects for estimating the operator intent, it would improve it many times, I think. Dus from the CAD model of the product, we have the relative positions of the different parts when they are assembled together, and based on that information, and when we are able to track the movement of the different parts, we could infer if the assembly operations was performed correctly by the operator. So at this moment we have no feedback loop, or we can't observe if the operator correctly performed the assembly operation. But yeah, your research could maybe improve my research. So the question is about whether or why we chose for the human interface made for Arcade for future work. First of all, because it's a great sensor, it's an industrial system. It has shown its capabilities in industry for many companies. So that's the first reason. And the second reason is that in last year, in the context of a master thesis, two master students have developed a ROS driver for this camera, this sensor. It's not only a sensor; it's more than that. It's actually an operator guidance system. It has its own software application, but we only use the depth camera inside it, and it has a robust algorithm. So that's the reason why it's an industrial, robust system. Thank you.
Die staat nog aan. Ja, okay. Good day, everyone. My name is Peter Aerts, and I'm also a PhD researcher at ACRO. And I'm going to present you something about map building in changing environments using object recognition and semantics. But first, some context. Most of you know what a mobile robot is, right? It's a robot that is capable of moving within its own environment or within its surroundings, and it's not fixed to anything. So mostly it's a wheeled robot that can move around in open space. They usually can be teleoperated or fully autonomous, or just autonomous, partly autonomous, and they also contain sensors. There are two types they mostly contain. One is proprioceptive sensors like encoders and IMUs to measure the internal state of the robot. And we have exteroceptive sensors like cameras and laser scanners to detect the surroundings of the robot, so to view the environment. Now, the use of autonomous guided vehicles, fully autonomous robots, is strongly increasing in lots of areas. For instance, in the medical care, like autonomous wheelchairs, but also for mapping roads and verges, but also in your daily house or in your daily lives. For instance, autonomous lawnmowers or autonomous vacuum cleaners. And also for inland shipping, so logistics sector is a big part that uses autonomous guided vehicles. Also for order picking, like Amazon does. But how does an autonomous guided vehicle operate? Well, first of all, it has a predetermined map that is known, mostly the geometry of its environment or some beacons. Next step is that he uses his sensors and the localization algorithm to know where he is within the environment. So he will estimate his pose within the environment and then uses a planning algorithm to move from point A to point B. But what if the robot does not know what his map is? What if there is no initial information to go from point A to point B? Well, entering the world of SLAM. SLAM stands for simultaneous localization and mapping. Yeah? So basically the problem is that if you want to build a map, you need the robot's location. But if you want the robot's location, then you need a map. So it's like a chicken and egg problem, right? So simultaneous localization and mapping tries to solve this by first localizing the robot within a partial map and then adding new information, the mapping process, to its already existing map. Now this technique is something that is being researched quite a lot already. and is still ongoing since the late 80s. But the important thing to know is that once all the robot locations are known, then mapping becomes fairly easy because then it's just plotting the data according to the poses of the robot. This is an example of mapping. So we see all these red dots are laser scans or laser scan data, and while the robot moves around, it adds new information to this map, right? So as you can see, it enters a new environment or a new space and then maps new data and adds it to the existing map already. Now, popular approaches have some limits. Mostly they assume that the environment is completely static, so that there are no dynamic objects within the environment during mapping. So they focus mostly on static geometric info, and if there are dynamic objects, they try to treat them as outliers, so they try to ignore this information. There is a subclass of SLAM that creates higher meaning maps, but they limit themselves to classifying objects and places. So they identify objects and places, but they don't do anything with this added information. Now, there are several techniques for SLAM. One of them is the Kalman filter, which predicts the current state vector of the robot and then updates this prediction using its sensor information. The particle filter also predicts and updates the current state vector of the robot, but it uses multiple hypotheses, so there's more than one option and it chooses the one with the highest weight, so the best estimate as being the current best pose of the robot. But these are recursive approaches, meaning that they ignore all previous data. They build on their best estimates from their previous iteration. There's a third part, which is graph-based optimization, and graph-based optimization tries to solve the full SLAM problem. So in this case, it uses all information from its sensors over all poses and features to optimize a graph and find all optimized robot poses. So this is a batch approach. I'm not going to go into the recursive approaches, I'm just going to focus on the graph-based optimization because that's also what my research focuses on. The graph-based optimization uses a graph to represent a problem, and every node in the graph corresponds with a pose of the robot or a landmark feature. And every edge between two nodes corresponds to a spatial constraint between them. So here we've got X given the robot poses and L giving the landmark poses. And of course the constraints between them, Z the measurements and U the actions of the robots or the motions of the robot. And what the graph-based optimization approach tries to achieve is to minimize this cost function. So basically we have the first term, which is the anchor term. The first pose of the robot needs to be fixed to be able to optimize its complete path. And the second term relates to the odometry or the motion of the robot. So these are the links between the consecutive robot poses. And of course, the last term are the measurements to the landmarks. So this is a better representation of the cost function. Here you have every constraint given between the robot poses and towards the landmark. These are also called soft constraints. Why? Because you can represent them or think about them as being springs, and that you try to solve this whole graph by minimizing the energy needed for all these springs to get the optimal robot pose. An example of this is shown in this video. So this was recorded outside the Technology Center building in Diepenbeek. I don't know if yeah, okay. So basically the green dots are feature points. The blue dots are the optimized robot positions, and the red ones are the robot positions of the odometry alone. And as you can see, SLAM works pretty well until now. And why is that? It's because at that point, the SLAM algorithm loses features. So it doesn't have any new features or previous features to be able to localize itself upon. So that creates a problem, because then we, as you already saw, then our mapping doesn't work. Yeah, we run into some problems. The question is, in this case, there's a person also walking within our data. Can we use these dynamic objects to better localize ourselves? And that's when I come here at graph-based optimization with dynamic objects. So basically the idea is we take the current approach, yeah, so we still have landmarks and we still have our robot motion information, but we add measurements to our dynamic objects. But not only measurements to our dynamic objects, we also include the motion between our dynamic objects. So we expand our cost function, which is usually solved using a Gauss-Newton method, and we add these last two terms, yeah, where the first one is the measurement towards our dynamic object, and the second one is the constraint between two consecutive poses of the dynamic object. So we did some experiments. So we started off with a simulation. We created a simulation in Python, which included a robot and a dynamic object, just to check or to visualize and check if it's possible to be able to localize yourself using dynamic objects. We also have written a SLAM algorithm to create a graph using a G2O package and to solve this one as well. Here you see an example of some pictures you're going to see in the rest of my presentation. The most important thing that you need to know is that green, or the green dots, are the ground truth robot positions. The blue ones are only of the odometry, and the black ones are the optimized poses. Yeah? And of course, as I said before, we also include the motion of our dynamic object. Why do we do that? Because if we don't do that, then you have like this first graph. We have no added information. Every measurement to a dynamic object is just a static measurement. There is no link between the robot pose and the next robot pose if we do not add these measurements between dynamic objects as well. So as you can see, without movement measurements, our optimized pose completely follows the odometry, while if we add these movement measurements, then our optimized pose follows the ground truth of the robot poses. And we did several experiments. So first off, just the hallway problem. The hallway problem is something fairly known in SLAM, because if you are driving with your robot in a hallway, then you generally don't have many features. But if we have a dynamic feature and we know or we can estimate its trajectory as well, so we have this movement and we can measure this dynamic object as well, then you can see that the robot poses can be optimized as well as the poses of the dynamic objects. So in this case, we've added just general Gaussian noise or white noise to our robots and also to our dynamic object. So basically, we added random error and we compared the robot poses, the error to the ground truth. If we look at the odometry and then the optimized poses, we can see that there's a optimization which is fairly good actually. Even if we add more and more noise, it's still able to optimize the robot's trajectory. Now, the dynamic object does not need to be static, does not need to be dynamic. It can also be partially static. So when the object stands still and then moves further along, this also works in this case. So we add our movement constraints as well from the dynamic objects. And as you can see, we can still approximate the ground truth of the dynamic objects as well as the robot. As you also can see, these are two separate runs. Yeah, so and here we go around the object when it's static, and in the second image you can see that we're going behind the object. So these are two separate runs, but for visualization purposes, I've put both videos in the presentation. And again, by increasing the error, you can see that we've got some weird trajectories from the dynamic object as well as the robot, but we are still able to approximate the ground truth positions. It's also not just limited to one object. We can also use multiple objects within this technique to optimize the robot's poses as well as the dynamic poses. Here in these graphs you can see that we've added more and more noise to such a process. So we have we've had 5 trajectories randomly chosen and then optimized the robot's poses. And as you can see from the first 2 graphs, the robot's positions of the error of the robot's position compared from the ground truth to the odometry is fairly high and keeps on rising. But of course, when we optimize or use our graph-based optimization, then the error drops significantly as well for the robot's poses as for the dynamic objects poses. This is, of course, with a fixed Gaussian noise, but when we introduce random Gaussian noise, then we have these graphs, and as you can see, the blue one again is the graph which shows the error of the robot's poses against the ground truth, so the error of the odometry robot poses. And the red one again gives the optimized poses. And as you can see, we still have a decent optimization up until a sigma of 1.1. Then we can see that we have errors or spikes in our optimization errors. We also tested this with real data. So basically, again, just one dynamic object and no landmarks. Yeah, so we still try to figure out what are the optimal robot positions and the optimal dynamic object positions. which is, of course, again, this formula. This is the same formula you saw on previous slides, only the constraint to the static features is left out in this one. And for our experiments with real data, we used a differential drive robot, which here is the model of that, of its motion. We used a laser scanner with this measurement model, but we did some operations to include a full pose of the dynamic objects. It's not only X and Y positions in 2D, but also its orientation. And for the last part, so the motion of the dynamic object, we incorporated a Kalman filter or an unscented Kalman filter to estimate its velocity and linear velocity and angular velocity for its motion model. For our experiments, we used a turtlebot with an Hokuyo laser scanner, and we only incorporated the encoder data of the turtlebot, so not the IMU data. And the dynamic object for our initial tests was a wheelchair chassis with a safety vest. Why a safety vest? We used the reflective stripes in order to get the orientation of our dynamic object. And we used the MarvelMind ultrasonic positioning system as a ground truth system. So it has a accuracy of around 2 centimeters, which we used as ground truth information. But in these pictures you can see what the effects are if we only use a dynamic object. So in the first picture you see all laser scans transformed using only the autometry of the robot, and in the second graph you can see that the map is much better when we incorporate the dynamic objects. Also in 6 different runs we get results that show that we can optimize the robot's position using dynamic objects during mapping, or include this information in our graph. Now for future work, of course, we can use Mask RCNN or other software to identify these dynamic objects, and use this information as well to incorporate dynamic objects within our graph, so that we can optimize the motion model as well as predicting or estimating the motion model parameters. So thank you. If there are any questions, I will be happy to answer them. So the question is that if for the hallway problem you always need one or something moving through the hallway in order to resolve the issue, right? Depends on what you think is the issue. If you want a perfect map, then the hallway problem is a problem because you don't have any information, so the map tends to drift and your hallway will not be right. And this can be and this technique can be helpful to solve that. But if you want to just avoid collision, then it doesn't matter, of course, if your hallway is straight or not, right? So if you want a better representation, then this technique can help. There are also other techniques like loop closure that try to solve this issue as well. So when you revisit the same place, then you know that you have made a 360-degree turn, and then you can correct where necessary. And at such places with less features, those are the places that usually get the most correction due to the fact that there's only one measurement there, so there's not much to prevent or to satisfy the graph there. So. So the question is if that if you have two robots randomly driving around, if they can build a map sufficiently enough or accurately enough. In principle, yes, this is possible, but the challenge would be to continuously estimate the model parameters of the moving object, right? So that's something you need to watch out for. If it's moving in a straight line and you can detect it, or you know this in front, up front, then you can localize yourself on the dynamic object. But if it's going to move randomly, then it can cause issues. Yeah. So I forgot to mention in my presentation that we consider a fixed velocity motion model. So. Yes? Okay, so the question is why I chose for graph-based optimization. Basically because that's the most promising technique that there is at the moment. Kalman filter and particle filters are still used today. But they are prone to, if there are large errors in measurements, then it can be tricky to get back on the right track of your robot positions, right? So basically graph-based optimization takes into account all information it has gathered. So it's I use that as a starting point because it's more robust and yields, in most cases, yields better results. So the question is that in my simulations I mostly show linear movement. Is it possible to have other forms of movement like circular motion and stuff like that? The answer is yes. Once we have these parameters from the motion model and we can incorporate this in the graph-based SLAM, then this would be possible. An example is, excuse me. An example is with our real data experiments, it was not a linear motion, right? It was a circular motion, so we have linear velocity and angular velocity in both cases. Where is it? Almost there. So basically here, the blue line in the second image shows the trajectory of the dynamic object. So in this case, we had a non-linear a circular motion. But random motion, yeah, it would be possible, but in this case, to estimate the parameters of the dynamic object, that would be the challenge, because they would change when you have random motion, of course.
Mm. How to, I have a question, how to display the different, yes, that's nice. Mm. Mm. Hello everyone, my name is Hui Zhang, and today I'd like to give my presentation with the title of Random Picking of Unknown Objects with dexterous vacuum gripper. And my research will be presented with the following 5 items. First, the research topic. What means the unknown object? The unknown object means that the 3D meshes of the objects are unavailable or unknown for the robot. And this slide lists the main challenges for the random picking of unknown objects. For example, the pose estimation, gripper selections for different objects, the grasp region selection in a dense cluster, and the uncertainty deformation and friction during the grasping. Of course, if the objects on a conveyor belt, then computational complexity of your grasping method is also very important. And the existing methods for the random picking for unknown objects can be divided into 3 categories. The first, based on the primitive shape, we can extract a primitive shape for the object and calculate the feasible grasp region based on the primitive shape. This method does not work well for a complex object. And the second method is, we can collect a lot of figures and mark the feasible grasp region manually, and use this data set to train a neural network to predict the feasible grasp region for the input image in the physical grasp trial. And the third method, you can believe it is the evolutionary version of the second method. The difference is that the third method trains the neural network based on the synthetic grasping example instead of the human marked examples. And this slide show you a brief flowchart of my grasping method. You can see that is a synthetic method. Here are 3 modules: grasp simulation, grasp quality prediction, and grasp execution. In the grasp simulation, the grasping example can be recorded by a point cloud or a depth image. And here you can see that this is the used dexterous vacuum gripper. You can see there is a soft gripping pen can deform to fit with the complex shape during the grasping. And today I mainly present grasp simulation and the grasp quality prediction in this framework. When we talk about my grasping method, the first question is why need grasp simulation? Actually, today you can find many open source data sets are available, including the 3D meshes and including a lot of images with the human marked grasp poses. You can use this data set to train a neural network. However, there is some problem. First, the existing data sets only fit a basic jaw gripper or vacuum gripper. Second, the marking feasible grasp pose for a dexterous gripper on the RGBD image or on the point cloud is challenging. And moreover, the feasible grasp pose for this gripper, this dexterous gripper, is often different from another one. So when you want to train a neural network, new network for a new dexterous gripper, you have to mark again. That is annoying. So we need a grasp simulation to generate the example. And as I showed you in the previous slides, this is the used soft vacuum gripper, and soft gripping pad can deform to fit with a complex shape. To analyze the shape of gripping pad to track its deformation, we should build a coordinate system. Considering the basic shape of the gripping pad, we can build a cylindrical coordinate system, and the whole gripping pad can be tracked by a set of triangles and their vertices. And notice there is the red text marked the key grasp region on the gripping pad, because in this region there are a lot of small holes, and this is a region to generate the air pressure differential between the object and the gripper. That is why the gripper can stick the object. So this region is very important. And then I proposed a 6-step grasp simulation to generate a grasp example. Build a geometric model, define the geometric restrictions, then we can track the 3D deformation. Then we can calculate a grasp range space vector and define the physical restriction for the grasping. Finally, optimize the vector to estimate the grasp quality. The following slides will show you some details corresponding to the 6-step grasp simulation, as I mentioned. First, the geometric restrictions. As I told you, the whole gripping pad is tracked by a set of small triangles and their vertices. So we can define a lot of restrictions for the coordinates of their vertices and for the whole gripper. Many restrictions. For example, the gripping pad on the side is possible go up and contact with the complex shape during the grasping. So we also need to consider this problem. So we need a lot of restrictions. And based on these restrictions, you can track the 3D deformation for the gripping pad. And then we can calculate a force torque range for the gripping pad. For example, there is a small triangles, and we can calculate the forces based on the air pressure, triangular area, the friction coefficient, the surface normal, and so on. And similarly, we can calculate Fy, Fz, torque Z. Then we can calculate the force torque range for the whole gripper. And in this process, there are 3 critical problems we have to consider. How to estimate the air pressure between the object and the gripping band. You know, when the object covers half of the gripping band or cover the whole gripping band, the air pressure is very different. So we need we need to estimate the pressure based on the basic fluid mechanics. And second, we have to track the contact area based on the 3D tracking principles. Third, we have to define the range of force torque range. You know, all forces and torques should be under the physical restrictions. So we need some knowledge based about the theoretical mechanics. Assuming that you solve all problems above, then we can define a grasp matrix for a virtual grasp trial. In the ideal case, if the gripping pad contacts a flat region, Fx, Fy, torque Z should be 0. However, in the real case, the contact surface is not flat. So you can calculate the force torque range by the summary of subforces and torques. And we can extract all forces and torques to build the grasp matrix, and extract all weight value to build a weight matrix. Then we can define the grasp quality based on the Euclidean distance between the real case and the ideal case. And this we can adjust elements in the matrix W to minimize the Euclidean distance. This problem can be solved by quadratic programming. Minimize this distance subjected to the limitations of a force torque range. Of course, subjected to the limitation of W. All elements, the summary should be equal to 1, right? And with this principle, you can generate a lot of grasp trials. This slide shows you 2 examples about the virtual grasp trials, about the trunking of the triangular surface, and the local point, which will be used to record the grasp. Okay, then we can generate massive grasp examples and then to train a neural network. So what's the function of a neural network? You know, in the grasp simulation, we know the 3D model. We can evaluate the grasp quality based on the 3D model. However, for a physical grasp trial, the 3D model are unknown. So we only know the robotic observation, that is a point cloud or depth image. So the function of the neural network is to learn the grasp principle to replace this function, replace the mathematical method to predict the grasp quality for a real-world grasp and draw a grasping quality map to find a physical region. In my neural network, I integrate the attention module because I want to let the neural network focus more on the critical region on the gripping pad I show you, marked by the red text, and because that region is very important to generate the air pressure differential. Here, this slide show you a brief flowchart, brief architecture of the GNCAN. It combines the convolutional block attention module and the classical ResNet. There are 4 ResNet units totally, and the whole network has 80 layers. Okay, and now I will show you part of the experience about my grasping method. First, the fine-tuning of the GNCAN. I try to change the depth of the GNCAN and change the channel of the REST units, the 4 ResNet units as I show you. And I find that the GNCAN with the 80 layers has a satisfying performance. And this figure shows you the gripping attention of a traditional CNN and our GNCAN. You can see that our GNCAN focuses more on the key region on the gripping pad, which is very useful for the further test. And this slide shows you 4 examples of grasp quality prediction evaluated by quadratic programming and evaluated by the GNCAN. You can see that the value is similar. And then I collect over 2,000 examples and then implement random noise on the input point cloud and predict the quality by the GNCAN. You can see that the red line is their standard quality, and the gray dots are the predicted value from the GNCAN. Then we can fit the gray dots by the polynomial regression, get the yellow curve. You can see that when the random noise is lower than 8 millimeter, the performance is good. The average error is about 5.4%. And for the physical grasp trial, I use this setup. In this setup, I mount 2 cameras. One is the static camera, and another one is the waist-mounted camera. Here I can show you a grasp example. You can see that the GNCAN can build a grasp quality map for a grasp trial, and also we can use the force torque feedback from the robot to detect the grasp status and adjust the approaching force. We can find the different states when the robot approaching to the object, pick up the object, and then put it down. And since no existing method available, no existing grasping method available for the used dexterous vacuum gripper. So I use the following the algorithm to implement the benchmark experiments. The first center means no algorithm. The robot always try to grasp the cluster center. And second is the minor revised DexNet. That is a grasping method for basic vacuum gripper. I have to revise it. And the third method is a traditional CNN. And the final method is our GNCN. We defined the difficulty of the physical grasp trial into 9 levels, from easy to difficult. You can see that our GNCN perform better, and which means our grasping method can dig out more potential of the dexterous vacuum gripper. And in this figure, are tests. I predict the grasp. I detect the feasible grasp regions with different methods and manually move the robot near to the object to take this picture. You can see that when the object stacked on each other, our GNCN can find a better grasp region for the physical grasp trial. Here is a video presentation. You can you can see that in every grasp trial we can build the quality map. This is a shoe, my shoe. This is an electrical drill. I think that is an electrical razor without hand. This is a field grasp trial. Yes, because the part of the object is out of scope of the camera, so yes, that is a field grasp trial. Yeah, it's not a perfect, but successful. Okay, the reminder is similar, so I'd like to go to the next page. Okay, the future work. My future work will mainly focus on 2 aspects. In a short term, I will finish the random picking test for the dynamic and multi-viewpoint grasping. For example, there is the existing method for the dynamic grasping, and this is our method. It is a closed-loop control run by 50 Hertz. You can see that the robot, the gripper can track the movement of the shoe and grasp it. And in the long term, I want to develop a grasp planning method for a bio-inspired grippers, which is available in Acro. You can see this gripper and this animal share the same grasp principles. So I want to develop a grasping method based on my framework for this gripper. And of course, I want to improve my framework by the following method. You see that, as I mentioned, in my current method, the grasp principle only learned from the synthetic data set. But in the future, I want to let the system can improve by the physical grasp trial. That means online learning and online grasping. Okay, thank you for your attention. And looking forward to your questions. Nine? Nine. Yeah. Yes. Actually, you can define the restriction at first, and then calculate the grasp range space. Okay, sorry. The question is why not calculate the grasp range space vector at first, then define the physical restrictions. Actually, these two orders can be switched. You mean that I should define the restrictions at first, then calculate the range space vector, right? I think, yeah, that is better to be understand, but the final result is the same because the grasp quality is optimized based on the weight matrix. Yes. Yes, I think your suggestion is very useful because switch them is easy to be understand. Thank you. If you go to slide 17. 17. 19. You mean the success rates, right? I do by myself with my own setup. So, yes, they have their own success rate, but I test with different objects, so I have to do again. So you use the different methods on our setup? Yes. How many times did you do? Each level, 50 objects totally. 50 objects totally. Yeah. So, but for example, the success rate lower than 33. That means that it cannot be. It always failed. So I gave up the count. So that means that is why the success rate is lower than 30%. If you have 50 objects, how can you get a success rate of 91%? That is around. That is not 50 objects. Each cluster is 10 objects, and I try to grasp it one by one. For example, 10 objects successfully grasped by 11 times. The success rate is 10 divided 11. So that is the reason why the number looks strange. Yeah, it should be odd number or even number like that. I understand because I use a different way to count the success rate.
It's important to also mention the way you got to these numbers.
Okay.
All of these were on experiments.
Yes. Rafa and Eric. Yes. Yes, that is a. Yeah, your question is how can I use two cameras, right? The question is why do I need another camera, the VIST mounted camera, right? The VIST mounted camera is used for dynamic grasping.
Hallo.
Yeah, that one. And this one is also okay. Also work. Also work.
Die is ook uitgevallen. Hetzelfde denk ik.
Ja, ik denk het. Ja.
Continue. Okay, the waist mounted camera is mainly used for the dynamic grasping, because in the dynamic grasping we should track the movement of the object as much as possible, and if the camera move with the robotic waist, it can track better. So of course it can be also used for static grasp. That is possible.
During the past years, I've seen a lot of presentations on conferences where they apply machine learning for this problem, for this problem, for this problem.
Yes.
And to me, it's not immediately clear where the difference lies between, or what actually the research contribution is of all of these different problems. So what part of your technique is like a general reusable research contribution, and what part is actually just a neural applying an existing machine learning technique to a new problem?
Okay. Okay, I can tell you. Actually, for my grasp planning method, the most important is grasp simulation, not the neural network. And for this in this slide about the architecture of my GNC and the CBAM from other researchers, and so I just use them and combine them, optimize them to fit with my application. My main contribution is here. Wait a minute. Here, the grasp simulation, is how to generate the massive grasp example to train the neural network. That is different from the research topic in the field of computer vision or the machine learning. Yeah, they focus more on the design of the neural network architecture, but my research topic focuses on how to simulate, how to evaluate the grasp quality in the simulation, and how to define a good human design principles to evaluate it and generate data sets. As for the architecture of CNN, I focused less. Thank you. This selection, right? Without saving.
Misschien kunt jij beter deze even gebruiken afhalen. En ik. Ja, je moet dat... Wacht. Deze misschien open doen. Ja, Google Meet.
Pagina
Okay. Um, uh, Good afternoon. I'm going to give an overview of my PhD. My name is Rafael Verbiest. I'm a PhD student at Acro in Diepenbeek. And my topic is about the automated object manipulation in fruit orchards. I will start with a small question. Have you ever asked yourself which amount of effort is needed to provide that one apple you buy in a supermarket? Well, this is the topic I'm going to talk about. I will start with a short introduction about fruit cultivation and where are the needs of the sector. Then my research comes in with the objectives to find a solution for those issues. And then I will start talking about a small part of my research about automated pruning and the branch detection system for that automated pruning. And finally, I will end with a research plan for the next months, because that will be an important part of my research, but I will talk about that later. Okay. Just in general, an orchard, to maintain an orchard, there are a lot of tasks to be performed. I listed them on this slide. It starts in winter, where the trees has to be pruned so that you can manage the structure of the tree, so that you can cut away the old branches and the diseased branches, and clean up the orchards in general. In spring, the blossoms starts to blow, the fruit starts to grow. It's almost a poem, but it's actually very serious for the fruit cultivators, because at that point they have to manage the maximum fruit load for each tree, and that's done by the thinning task. Also, when the first leaf starts to grow, the trees become vulnerable for diseases, some insects, some infections. So from that moment on, they have to start spraying with plant protection products to protect those tree and the orchard. And they have to do that until the end of summer, when harvesting season starts. Then at that moment, it's the most important task to harvest the yield of the year. And it will continue until the end of fall. So those are all tasks that have to be done to provide that one apple. Together with PC Fruit and activity research was performed, and as you can see, all these handlings need a lot of labor. All that labor is performed manually by seasonal workers, and you can see that it's a huge amount of labor, especially for the picking part, followed by the pruning and the thinning. All these tasks are very labor intensive. So those are the needs of the sector. There is a too high amount of manual labor that has to be performed, and there is a lack of skilled workers, because the seasonal workers from abroad are not coming to Belgium anymore. And there is where my research comes in, because I think that automation could be a solution for these parts. So I did a general literature review to state out the state of the art, to see what already has been performed in research. And this combined with those needs that were on the previous slides, I decided that there is the highest potential to do some investigations about automation of pruning and of the thinning task. So in my PhD thesis, my PhD research, there are two main blocks, as you can see in my work package diagram. On the, where is my mouse pointer? Yeah. On the left side, you can see in the light blue the pruning part, and on the right on the right side, the thinning part. Today I want to discuss whole this scheme, but only one part, namely the sensing part of the automated pruning. And this is the branch detection algorithm I've designed in the last couple of months. Because before you can actually prune and cut a tree, you have to know where are the branches, where can I cut, and of course, what is the best place to cut. So therefore, you have a branch detection algorithm. It exists out of some major blocks. We start with data collection. I used time-of-flight cameras, so the data that has been collected is point cloud data. The raw data always has a lot of noise and other things that have to be removed. So the first step is a pre-processing of that data. And when that is pre-processed, there is one big point cloud over the tree. Of course, we want more information and details. So the first step after that, so the second step in total is the clustering step, to cluster that big point cloud into small parts to extract some information. And that extraction of information has been done by a line fitting algorithm to find the direction and the position of each part of the tree by fitting one line. Most of the times, those clusters and lines that are fitted are not very good. They are just a rough estimation. So the first step is to optimize those clusters and lines based on the first estimation. And in the end, we can estimate the total three-dimensional structure of the tree based on those optimized lines. Now I will dig deeper in each part. As you can see on the picture, it's not very visible, but this is my tree, patient 0. It's a small pear tree in the gardens of Acro. It has just one trunk and 3 simple branches with a diameter varying between 5 and 23 millimeters. And of this tree, I made a scan with a time-of-flight camera, namely the Kinect Azure camera. This is the scan. So you can see the tree in the middle, also some parts of the surroundings, like the ground, and of course in space you see a lot of noise. So the first thing is to clean this up. The pre-processing part exists of 3 major blocks: the statistical removal filter for the noise filtering. Then I remove all the physical elements of the surroundings, and at the last part, I do an ICP scan matching algorithm to stack the current scan on the previous scan so that all the information can be stacked on each other throughout time. Okay, so this is the outcome of the first this step. So we can see that all the surroundings are removed. There is a little bit noise, but still okay, that's manageable. The next step is to cluster that big point cloud that you could see into smaller pieces. I did it in 2 major blocks again. First, I detected the trunk with cylindrical segmentation, because if the trunk is segmented, we can temporarily remove it from the point cloud, and then all the other branches can detach from each other, so it's easier to cluster all the branches with an Euclidean clustering algorithm. This resulted in these clusters for this patient 0, and as you can see in the bright red, the cluster of the trunk was detected, and then all the other parts are in other colors. And as you can see, sometimes 2 branches were clustered together, so it's not optimal, like I said previously, but okay, we will try to optimize this clustering. But first we want to know some information about all these clusters, and that I did with a RenSec line fitting algorithm. So for each cluster, one line, the best fitted line was fitted. As you can see in the bottom, sometimes it is very good, represents the cluster very well, but for example, this fork of the two branches, it's still a problem. So the next step is to optimize those clusters and lines. And for this, I wrote my own split and merge algorithm, the CPP, split and merge, standing for central perpendicular plane split and merge. Why I don't just use the standard split and merge? Well, as you see in the right image, you see the fork of the two branches that were clustered together. The yellow line is the Rensack fitted line. And a standard split and merge will start with a baseline, namely the red one, and searches for a splitting point. It's there in the corner, and then the new lines will be defined based on the start and end point of the baseline and that splitting point. And it's no good result at all. As you can see, it's even worse than the Rensack fitting. So my algorithm has the advantage that it's not basing the new lines on the previous line, but it's splitting the point cloud into smaller clusters and then fits a line through each cluster again, and it gives a much better result, as you can see in the bottom picture. I made no assumptions at all for this algorithm. Some relative work they think about a structure and base their algorithm on that structure, but mine is generic as I could make it. So it's possible to find all the structures, each structure that you can imagine. However, when it becomes too complex, and that is one of the disadvantages, that it will fail. But okay, I will try to manage in future work, of course. The last part is to estimate the three-dimensional structure out of the lines that were fitted in the previous slides. Just all those lines together we have a bunch of lines, and now the next step is to attach all these lines into a line structure. And when that had happened, the thickness of the branches has to be estimated, and after that, the direction of those lines together with the thickness can form a three-dimensional structure. However, those two last steps are in light gray because it's work in progress. But the line attachment algorithm was written already. I wrote it already. And this is the outcome of the algorithm. And as you can see, all the lines were attached to each other in a nice structure that represents the tree very well. Just for the show, I fitted some cylinders in it, but normally you have the thickness that you need to estimate the thickness. But there, on this picture, you can see how the three branches are going, and if we compare it to the actual picture, you can see that it's a pretty good estimation. However, here and on the attachment points of the branches, there are some problems, and that's because there some gaps were occurred in the point clouds. So there was a lack of information, and the algorithm could not handle it quite well. But still, it is a really good first rough structure, as we can conclude out of this branch detection, especially with the comment that it's a very sparse point cloud. These point clouds had only 2,000 or 3,000 points, and in related work, they work with point clouds of more than 100,000 point clouds. So still, this algorithm works, and that's why I call it a robust algorithm. Also because I had no assumption of any structure in the beginning. Another conclusion about time is that the total calculation time of my algorithm from the start of the scan until the end where the line structure was given is 26 seconds, which is comparable with related work, only the related work that reported some time studies, because most of them are too slow or too computive intensive, and therefore they do not report time studies. So for the ones that do, I'm already in competition with them, and this with a not optimized algorithm, because there is a lot of space to progress. I have to optimize all parts from the beginning with optimizing the scanning parameters until the end for the attachment algorithm. So that's one of the points in my future work. Also, of course, ending that fifth block by determining the thickness of the branch and end that three-dimensional structure. It's also a point in my future work, and to implement this branch detection algorithm in ROS so that it can be combined with the robotic controller and the pruning tool in a total pruning unit that can work in an orchard. Okay, the last part is the research plan. So why is it so important that I talk about this today? Well, next winter is pruning season, and it's one of the most important moments in my PhD because this is the moment that I can test my branch detection very intensive, because all the leaves are from the tree and I can test it in a real orchard environment. I want to test the branch detection algorithm on different kinds of tree structures to determine which structure is the best for robotic pruning, and of course to optimize the parameters that I can find the best combination between the tree structure and the algorithm parameters. So optimization is key in the end of the winter. And of course, I also want to test my pruning tool. As you can see in the picture, it's a conceptual drawing of a pruning tool that will be combined with the branch detection algorithm into a total robotic unit. So also for this, I need the winter to do an intensive time study and test the usability of the whole system in an orchard environment. Okay, this was my presentation. Thank you for your attention, and if there are some questions, I'm pleased to answer them. Yeah, the question was that if my branch detection algorithm works on other point clouds, or did I test it only on patient 0? Well, at this moment, I tested only on patient 0, but as I told in the future work or in my research plan, in winter I will test it very intensive on a lot of different trees and a lot of different tree structures. It's only, the question was if it was for every kind of object or only for trees. This is specifically for trees or tree-like structures. Yeah. Yeah. So the question was that what if trees are intersecting to each other? How well will the algorithm react on this? Well, I did not test it yet, but as long as the points or the branches are not intersecting closely and the point clouds are detached from each other, probably it will be possible that my algorithm will detach the different structures. But it has to be tested. Like I said, I did this algorithm in just a few months. So it's not tested yet, it's just a first version. Yeah? Okay, so the question was, when you are scanning the tree in different distances, the point cloud could change a little bit. Could it react on the performance of the algorithm? Well, that's why I use ICP scan matching. So every scan will be matched on each other, and those small differences will be filtered out by combining it together with different scans previous. And normally, yeah, it will handle it. Yeah? Yeah. So the question was, several years, in 2006, I think, Acro designed a picking robot for picking apples, harvesting robot, but it never break through. Why didn't it break through, and why would I break through with my robot for fruit cultivation? Well, they didn't break through because it was very slow in first place, and it was pretty expensive because robot arms are pretty expensive, and they just used it only for picking. But if you, I will go back in my slides to my, there. In my work package, I didn't discuss it, but in the last part, there is an integration work package where I integrate my pruning part and my thinning part together with a spraying unit and a picking unit on one mobile platform. That mobile platform will be multifunctional, so that one robot arm that is pretty expensive can be used not only for that picking part in 3 weeks a year, but it can be used throughout whole the year. So it will be more profitable for the fruit cultivator. Labor and yeah. Yeah, but you have to see it in perspective, because that amount of labor in for the picking part, that 60% has to be done in a few weeks. So that's the problem that it's very labor intensive. The pruning part, for example, can be done in a few months. So it's less intensive in the concentration of labor. So it can be used throughout whole the year if you combine it together with all the other tasks. Yeah, two, yeah. Yeah, true. And if the robots are there for pruning and thinning, why don't you use it for picking as well as an extra help? Because probably for picking it won't be profitable to only use robots. You will combine it with seasonal workers, but there is a shortage. So it's okay. Another question? Oh yeah.
Okay, so I'm Bart. I'm also doing my PhD with Acro in Diepenbeek, and my PhD topic is robotic sorting and manipulation of waste streams. I will first introduce my topic a little bit more, and especially why sorting is needed. My research is mainly applied on aluminium waste stream, of waste in general, and why is sorting needed actually? At the moment, recycling is actually meaning downcycling or degrading aluminium. This is because primary aluminium used for all applications, high grade or high quality applications as well as low grade applications, is recycled. And within this recycling process, all the aluminium types are combined and mostly reused in applications for low grade aluminium. And because of this downcycling or this degrading of the aluminium, forecasts show that in the end, because of this evolving degradation, there will be like a surplus in this aluminium waste that we're not able to use anymore in new applications, and therefore we need to sort. Because if we sort this aluminium, we can keep like the primary aluminiums together, the high quality aluminiums together and the low quality aluminiums together, and therefore recycle them to be reused in like the same grade applications. But for sorting aluminium, you need like a special sensor. Why? Because like the human eye cannot really distinguish the grade of aluminium because they all look alike. And the sensor, it can be multiple sensors. I will talk about this later. But when using a sensor, you also have digital data, and it would be a waste if you don't use this digital data to automate things. And therefore, my research questions is arising: how to integrate a robot in a waste sorting system. For my research, I need some hardware, and the hardware I'm using is a 5-meter long conveyor belt with a servo motor to control the speed of this conveyor, 2 robots, a SCARA robot, which I'm mostly using, and a 6-axis bigger robot that's currently not used, a PLC, 2 cameras, of course a gripper device to be able to pick an object from the conveyor belt, a SIG encoder to detect the movement of the conveyor belt itself, and maybe in a later stage of my PhD also a LIPS sensor. So my research is consisting of 3 main pillars, the sense pillar and also the think and the act pillar. Within this sense pillar, the state of the art is normal object recognition, so just seeing an object, recognizing that the object is there, and getting information like the location and the orientation. But within this research, one of the research topics is using computer vision to classify this object into a certain aluminium type or grade. and maybe libs integration. Within the think pillar of my research, the state of the art is a static conveyor speed, normal grasp port estimation to define a possible pick on this conveyor belt, and then a sequence planning based on time to be able to pick as much pieces as possible. And the research topic that I'm going to work on within this pillar is adaptive speed control, to be able to pick as much as you can, like through the complete system throughput, or the complete timeline, let's say. So you can save time when there is nothing to pick, and you can use this save time later when there is a lot of items to pick. And like a sequence planning, so the planning to pick like a certain order of objects based on other criteria than time. So maybe weight or like a certain grade or type of aluminium. And then the last pillar of my research is the act pillar. This is the pillar in which we try to do something with the objects that we recognized. Normally, the state of the art is that there is only one universal end effector in this robot cell. And within my research, I would like to see if it's possible to combine different grippers, like in their advantage or in the combination advantage. And then also, if we can design specialized end effectors to be able to pick a certain type of waste in a good way. So 3 main pillars. The sense pillar is mostly researched by 2 of my colleagues, Dylan and Simon. Dylan is focusing on the advanced computer vision, and Simon is focusing on LIBS, light-induced breakdown spectroscopy. And my research is mainly focusing on the think and the act perspective of this sorting problem, as I explained before as well. Now I'm going to talk about what I already did during my PhD. We built like a test setup, so the conveyor belt together with the robots, and we mounted a camera system to be able to detect the objects and like to start developing some algorithms to be able to handle these objects and the sorting itself. And to do something with the information we got from all the inputs and outputs, the inputs actually, we also needed to design a certain communication structure, because we use a lot of different brand hardware pieces, for instance the robot and the cameras. We also need a way to synchronize them and also a way to let them communicate so the information gets centralized and we can do something with all this information. As you can see, I use different colors for all the different types of communication, and there are a lot of those different types of communication, so it was quite a challenge to make them communicate and work together. As you can see as well, the encoder signal is read by the robot. This robot generates, reads the signal, so it knows the conveyor speed, and generates a trigger for the PLC. This is a periodic trigger of 800 millimeters. So whenever the conveyor belt moves to 800 millimeters, the PLC gets a trigger. And this more simplified trigger is used to synchronize all the other subcomponents, like the camera and the robot itself. Because the camera and the robot needs to be synchronized as well. Whenever the camera takes a picture, the robot needs to know exactly where this picture was taken and to be able to track and point at the right objects. All the logical information and the planning and so on is done within Python, for which I also designed the user interface. This is to show us what's going on in the conveyor belt, or to show what's going on inside of the computer vision system. As you can see, we have some fields to set some parameters, like the speed of the conveyor belt, and to start and stop the conveyor belt and the complete system, as well as the big picture in the middle, which shows what's seen on the conveyor belt. For instance, it could be that there are no green rectangles showing around the objects, and then we would know that something was going on with the vision system, which is quite useful. Then the vision system or the cameras get a synchronizing pulse from the PLC, and then the camera starts taking an image. This image is is a line scan actually. So multiple profiles are stitched together into an image with information of the encoder, and then this data is passed on to the PC, to the computer, in which the Python program, the vision program, is doing object recognition and calculating the location, orientation, rotation, the height, and all this information is then used into a sequence planning algorithm. In this sequence planner, the information of 3 frames is combined, so there is like a lot of data to plan. But before they can, the objects can be planned, a sequence planned, to have a good picking order. The objects need to be sorted, of course, because all the objects are laying on top of the conveyor belt, and you want the first object in the list to be the first object on the conveyor reaching the robot as well. So that's what we do first. We sort the object data based on the Y value. The Y value is the moving direction of the conveyor belt. And then we do a brute force calculation of all the possible sequences that are within these 3 frames. And if we have all the possible sequences, we compare the sequences on 2 criteria. One is the amount of objects within the sequence, and one is the idle time of the robot. Why? We want to pick as much pieces as possible in a sequence, so we take the longest sequence possible. And the idle time is important as well, because if we have 2 equally long sequences, we want to use the sequence with the most amount of idle time. The idle time is actually the time the robot stands still, and therefore, if this time is maximized, the energy consumption is minimized as well. And once we have a good sequence planning actually achieved, we encode this data and send it to the robot, so the robot can start picking whenever the objects arrive in the picking area of the robot. So the robot gets the information, decodes the data, and then starts synchronizing with the conveyor belt, as you could see with the in the video. So it's synchronized with the objects, aligns with the object, picks it, and throws it off the conveyor belt into the right orientation, so we can sort it actually. I have another video which shows a more real-time speed of the picking process. So you can see the objects are thrown the first one was thrown in the most far away bucket, and then the second one was in the first bucket, and the last one back in the most furthest bucket as well. So it's sorting, and it can do it on a real-time speed. My latest work is an economic potential estimate. I took a use case in which 20,000 tons of aluminium waste need to be sorted with a little bit more than 3,200 hours a year. Unsorted, this aluminium had a value of 1,200 euros a ton. And within this use case, we were looking at sorting in cast on rod, because normal computer vision showed to be able to distinguish those. And if you look at the graph, the most upper line is the setup for this use case. It's actually a scenario in which we use 2 systems with 6 robots each. And the system was able to sort this amount of material in 3,200 hours a year. And the return of investment of this system was less than 4 months, so it was quite promising. And the potential profit or the potential revenue a year is a little bit more than 3,600, almost 3,600,000 euros, so actually 3.6 million euros a year, which is quite promising as well. When more shifts are turned, actually, it worked actually, which is possible with an automated system, of course. Then future research activities, a returning conveyor belt, because right now we had to put objects on the conveyor belt ourselves. We are building a new conveyor belt, which you can see on the right, which is returning the scrap falling off the end of the conveyor belt, or the scrap that's picked off the conveyor belt, so it can be a continuous ongoing system, which is quite interesting for research as well. Then alternative planning algorithms and grippers. I talked before that the sequence planning algorithm that I plan to write could do other things as well than just optimize the amount of objects picked during a certain length of time. For instance, maximizing the picked mass could be an objective, or sorting in more than 2 waste streams, 3 or more, or some other criteria, eco points, you can name it. And then new grippers. During my PhD, I will try to find some new gripper designs, especially for a certain amount of plastics or small objects or big, very bulky metal waste pieces. And a good thing is also like comparing those grippers and seeing where like a gripper has an advantage over the other. Then the variable conveyor speed, I talked about this a little bit before. We see, like in the industrial applications, that the fill of the conveyor belt is never homogeneous. So sometimes there is like a big bulk of objects on the conveyor belt, and other times the conveyor belt is almost empty. And therefore, we think it would be very useful to slow down the conveyor belt at some point and speed it up at another point, which will create like a continuous like output volume of this system. Because we speed up and we slow down, the output of the conveyor belt will be always consistent, which could be very useful for another system. As well as the value is changing on this conveyor belt. It could be that there is only rubbish on the conveyor belt, and then you don't want to spend time waiting there to pick nothing, and you want to speed the system up so you can pick more valuable objects at a later time. So we will plan to use a vision system to see what the fill density is of the conveyor belt, and then, or a current value within a frame. And based on this, we will try to define the right conveyor belt speed. And yeah, like I said, lower it when there is more potential, and speed it up when there is no potential on the conveyor belt. Then LIBS integration. Why is this important? Right now, the vision system is only capable of separating cast and rod. So only cast and rods are recognized, but with a LIBS system, we could potentially be able to sort or classify in series. So actually grade types of aluminium. And by doing this, for instance, on a gantry or a 6-axis robot, close to the vision system, we could potentially classify or sort in more than just cast and rod. We could sort in more than 2 sorting bins, let's say. And also the created value would be higher. Before we saw that there was like an increased value of 150 euros a ton if you could separate in cast and rod. This could potentially be higher when we can sort in more than only these 2 end streams. And then load balancing. Like I told before, like only one robot is not that interesting in a system. We would love to implement more than 1 robot, for instance 6 for each machine. But if we implement more than 1 robot, we also have to balance the load in between those robots. And also, why do we need the load balancing in between these robots? Because we have more classes available. If we have, let's say, 5 robots, and the robot can sort in 3 bins, then you have 15 possible bins, so you can divide the load based on that. And also, you can get a higher throughput. And by load balancing, you also balance the maintenance requirement for all the robots, because they all work equally hard and they have the same maintenance requirements. What we also can do is mix different gripper types on different robots. And very important with that is also that this load balancing algorithm keeps track of which robot has which end effector, and assigns like a certain piece to the right robot, of course. And combined with all the previous research, this could lead to a higher efficiency and a bigger economic advantage in a sorting system. Thank you for your attention. And if you have some questions, please feel free to ask them. Cool. Okay, great. Can you repeat it, please? So you said that you think the conveyor belt will be distance of the Yeah. Yeah, so the question is that we, like I showed, sync every 3 frames or every 800 millimeters. And the real question is, if we change the speed of the conveyor belt, could there occur some slip on the conveyor belt drums, in between the drums and the conveyor belt itself, and therefore we could lose track? Yeah, indeed, that could be like an issue, but I don't plan to have very abrupt changes in speed. I would plan to change the speed more credible, and therefore the accelerations would be not that great, and therefore the slip wouldn't be that great of a problem. And also, synchronizing is on every 800 millimeters, and therefore only 1 meter of conveyor belt could be like with an error. And the conveyor belt's speed at this moment is 0.5 meter a second, so 800 millimeters of conveyor belt would represent a little bit more than a second, and therefore also this like loss of material, let's say, wouldn't be that big of a problem. Because also we are working with waste, so that's an advantage in this case. Yeah. Yep, so the question is, at the moment, we brute force calculate every possible sequence. Would it be a problem if there are a lot of pieces on the conveyor belt and therefore increasing the computation time? The answer is both yes and no. We right now take an image and process the image while the next image is taken. So we have actually 800 millimeters or more than, a little bit more than a second time for computing all those sequences. And also within my brute force calculation, I don't calculate every possible sequence. I only calculate the possible sequences. You mean like there are more mathematical possible sequences, but I calculate only the practical possible sequences within this new, this novel sequence planning algorithm. So I did tests with up to 260 objects within 3 frames, and the computation time was less than, I think, 0.2 of a second. So I didn't encounter any problems yet. Any more questions, Rafael? The question is, the acceleration cannot be that high, like I explained before to Ivo, because otherwise we would encounter slip. Is it then worth it to change the speed? I don't know. I didn't test it yet. That's why I planned to do it. But I talked with some recycling companies in Belgium, for instance, Galoo. And at first they were quite, let's say, stubborn or against the idea of changing the conveyor speed. But after a little while, they seemed quite enthusiastic about this idea, because they sometimes, they normally load their machines with bulldozers. So they pick up a lot of scrap and put it inside of the machine. And therefore they concentrate actually a big pile of objects on the same conveyor belt. And it could be, in their case, that there is 1.5 meter of empty conveyor belt space, and then 2 meters or something completely filled with objects. And by slowing down and speeding up the conveyor belts, we could even out this problem. And therefore, maybe another sorting system linked to ours could be fed with a more constant waste stream. So it could be beneficial for them in that way as well. I think we will plan to do some basic tests to see if there is some benefit on doing this. If not, yeah, then it's a good research perspective as well to show that it's not really beneficial to do it. So the question is how long it takes to do a ellipse measurement, like I showed here, and if it was possible to mount it on the gripper or the robot itself. The answer to this, to the first question is the ellipse measurement. I think they can do it at 100 hertz, so it's one measurement every 0.01 second, so it's quite fast. They can do hundreds of samples within a second, so that's not a real problem. And then mounting it to the robot, we can mount it. We prepared for it. I think we can do it. But the main question is, should we do it? And like I've been talking with colleagues about this, and right now we're thinking to implement the ellipse system on another robot, more in the beginning of the conveyor belt. So we have the information of the measurements early on, and we can use this information to plan accordingly, instead of having the information when the object is already within reach, because then we definitely will lose the object, because it's already out of reach before we get the measurements back from the analyzing. And then we need like another robot to pick it afterwards. So I think we will implement it on another robot more in the beginning of the system, instead of mounting it next to the gripper, like on the picture. Oui? Graphic user interface? Let's go. There you go. So the question is how we localize every object and how we fit, I do fit the rectangular boxes. This is actually the work of my colleague Dylan, but we use a depth image actually to recognize the objects, and we so at some point we have like no background and only objects, and then we fit a bounding box around the object and localize the center of this bounding box and use a center to pick the object. This is quite a primitive way of doing it. And we know that it's not the best solution, but at this stage of the project, it's just a starting point for me to develop my sequence planning as well. In the future, we plan to implement a more advanced computer vision and object recognition algorithm to be able to define better cross poses. And another part of my answer is I'm using a parallel gripper with a height-changing class, and it's a pneumatic powered gripper. So in our case, like the precision doesn't need to be that good, because if we are like, let's say 1 centimeter off, the gripper itself will will push the object in between the glass and we can pick it. And also, in case of like collision, the air pressure is not that big, so the gripper itself will not break, and the gripper will just stop on the object and will not be able to pick the object. But like I said before, it's waste, so if we don't accomplish a pick and the object just goes on the conveyor belt, that's not really a big mistake or a big, how do you say it, like a big error, let's say. I hope that answers your question. Okay. Okay, no problem, thank you. Any more questions? No more questions? Okay, thank you for the attention.
Hallo? Ja? Oh. Oké. Maar ik hoor mezelf ook 4 keer of zo. Hallo? Is het oké? Okay, thank you. Hello everyone. Thank you for having me join this day full of interesting presentations. Today I would like to present you the process of the development for suspension packaging for e-commerce, my PhD. My name is Wart Nika. So I am a researcher at the group ITL, which stands for Innovative Technology for Logistics. We're a group of 9 researchers all working on the e-commerce, which is a rapidly growing sector. And we put our focus to concepts which are open for innovation. My own research lies within the packing group. I'm pretty sure we're all familiar with multiple ways in which goods are packed, with some being more eco-friendly than others. The method I'm working on is placed in the middle of my slide. It's basically just a piece of cardboard, the tray, and we wrap it around the good that we want to ship with typically plastic film. So how this works is what you want to ship gets placed on top of this piece of cardboard. It goes through a wrapping machine and it gets automatically processed, ready to ship. On the left, you see what's commercially available. Those machines were used for long items like carpets or wooden beams to wrap them with this plastic film to protect them for shipping, but the machines are not really suitable for lightweight packages. So we bought this blue machine, but in the first months we decided that it was better to start all over and make our own prototype. The small video shows what we are capable of right now. It's a bit faster, but the main improvement is better control over the film tension. So I started my research with the following question. How can these horizontal wrappers be adapted for e-commerce goods, allowing for a random and arbitrary shaped package to be packed automatically in a sustainable and affordable manner? This method is not really new, but there is still a lot of room for improvements. The cardboard that is used is often too thick, so with a better machine we can reduce the cost of the cardboard, and also the foil that is used is often too much. One big issue of this packaging method is the bottom damage. When this package falls on the bottom face, the impact forces are still quite high, so that's not interesting when the goods are fragile. It leads me to some working points. The solution needs to be fully automated. The speed has to be quite high, and we want to be able to process a large range of products with one single machine. And all in all, it's for the e-commerce, so it has to be an affordable solution because nobody wants to pay for their shipping costs. So retention packaging is quite known. It's nowadays used for quite heavy items, but suspension packaging is more interesting because the precious item is fully suspended in every direction. Typically, it floats on 2 layers of film, and it offers shock absorption in every direction. But by just changing the piece of cardboard, the tray, we are able to offer suspension packaging with these horizontal wrapping machines. So what we changed is we added an air gap on the bottom face, and this allows for the shock to be absorbed in this direction as well. Also, we're trying to use paper instead of plastic film. This would allow for a very eco-friendly solution because every material that is used for this packaging method would be paper and cardboard. So our ongoing projects are split into two large groups: the small goods for the e-commerce, which are often lightweight items or can be multiple items at once. Typically, it's preferred to have an appealing appearance because the customer receives these goods and we want them to be happy. We also often want a high degree of protection, and as I already mentioned, a high throughput is required. With what I've learned on these small items, we noticed that we have quite a good knowledge that we can apply to this advanced retention packaging. So a couple of examples, what we can package within the small groups are like a cordless drill and a battery that gets shipped to a customer, or a hand mixer. And with the advanced retention packages, we have quite challenging shapes of heavy hydraulic motors or electromotors. And those still pose quite a big challenge with the existing machines, but I'll get back to that in a moment. So you might wonder whether this suspension packaging is a viable solution to or a viable alternative to what already exists. So we did quite a lot of tests, more than 350 drop tests, in which we basically just drop a box with our package, and our package was a shock recorder. So we measured the G-forces in our reference being the foam peanut flakes, which offer quite a good suspension. And then we compare those with 5 different variants. Some of them have really high impact forces, so we scratched those, but one of them really proved to be as interesting as the foam filled box, so we can go further with that solution. And for the heavy items, normally they get shipped inside a box filled with self-expanding foam, like you see on the left. It's really not interesting because it takes a lot of time, and an operator has to fill a bag with this kind of foam, then has to place it inside the box and then put the motor on top. So there's a lot of labor involved. We want to change it to retention packaging, but with the classic machines, it's not possible because there are really sharp corners on many of these objects. So with our new machine, we can change the foil tension, and we can lower the foil tension in specific regions to prevent the rupture of the foil where it normally would. This leads me to the machine that I developed. With closed door and with the hood open, I think with all us being engineers, it would be more interesting to dive right into the details. So this brings me to the inside of the machine. There are a lot of challenges. Most of them are related to the control of the tension of the foil. So here is a piece of small paper. It can also be plastic film. And this entire ring turns around and around up to 3 revolutions per second. And we want to keep a tight control over the film tension while we are wrapping. So we thought we should put 2 servo motors, one on the spool, one on the one called stretch roll, to control this tension, but that leads to a lot of requirements on the rotating ring. Basically, we need to know where the ring is, how fast it's rotating, and we need energy for this control and the motors to be fed. And a lot of auxiliaries, such as cutting the cardboard tray into the correct size before this machine. So you might wonder what can go wrong if you don't have good enough control over the tension when pulling upwards. I got this small video. I hope you can see it, but it's quite obvious that the package gets pulled up when the forces are too high. So that's why we want to pull softly when going up and apply tension when moving down. I've got this control loop scheme. Don't get lost in the details. I'll just handle some groups. I'll first start with the main block, being the real-time control loop. Then I'll handle some of the inputs, being a 3D camera, some calculations to be done before the wrapping starts, measuring the actual position and speed of the ring that is rotating, and then something about measuring the film tension. So first of all, the tension control. We have 2 servo motors, the one straightly coupled to the spool, and then optionally the stretch roll. When using paper, this one isn't actually turned on, and we only use that one, but I use the second servo is encoder to get some more speed information. So I put a load cell here and here to measure the film tension that is connected to the package being wrapped. And there are a couple of ways to control that tension. The most simplistic one is open loop, where you basically calculate the required torque on this spool by its radius to know the film tension. But because of friction and inertial torques required, that is not possible when the ring is rotating fast. So we quickly move to closed loop systems, where you use the load cell to adapt the speed of the spools. Better performance is achieved when you use the stretch roll. Oops, sorry, one back. Yeah, when working with film, it's more interesting to use the stretch roll to determine the speed of the film being dispensed, and then you use the closed loop system to control its speed, and the second spool would just become a slave of the other motor with an electronic gearing that determines the stretch that is available in this section of the film. But when you want to go even faster, like on this video, that is 3 revolutions per second. With plastic film, just feedback isn't good enough because the gains required would be too high. and become unstable. So I added a lot of feed-forward control, but for feed-forward control, you need much more information over the package that you are wrapping. So I added a 3D scanner to know which package we are wrapping, and I'll get back to those calculations. But like to show the complexity, this blue box here takes only 1 second, and in that second there were 3 turns of the entire ring, and during one turn you basically have the motor ramping up, ramping down again, ramping up, and ramping down again. All that to control the foil tension. Now it was with a constant set point of 10 newtons, with an error of only 6 to 8 newtons plus and minus. The most difficult part is low tension, because if the tension gets below zero, you're basically giving more foil than required, and so the foil goes everywhere, which is not what you want. So that about the wrapping. Then next slide, package geometry. I need to know which shape of package we're working with. So we've added Intel RealSense 3D camera on top of the infeed, which captures a 3D point cloud, and then we calculate the convex hull to know only the outside points that could be in contact with the foil that is being wrapped around, and then we cut angled slices, being the film that is well, the path that the film will follow when the package is moved through the wrapping tunnel. This does not only work with rectangular boxes, but also with more complex shapes, such as this cordless drill. Here I added many more middle wraps, so more turns that would be required if the package has to be retained much more than with just a couple of turns. So we have now more information of the package that will be wrapped. So now we need to do some calculations. I just used a typical box shape here, but this can be a more complex shape as well. Now these snapshots are taken from my calculations in MATLAB, but I migrated those to Python, so everything gets calculated on the on an Intel upboard right before the wrapping program starts. So this is the theoretical foil speed that is required to wrap this package, and I use this information to know how the shape of the profile of the motors should be during one turn, and then it gets scaled up and down with the speed that the ring is turning with. My previous video showed a wrap with constant film tension, but we can also adjust the required tension to be low when going up and high when going down, but that still has a lot of testing required before it will be finished. We also need to know the position of the ring, because otherwise we can't know where in this profile we are. And we also need the derivatives like speed and acceleration. So the best place to go and look for the position of the ring is in the PLC, which controls the ring. Unfortunately, the ring is on the standstill part of the machine. No, the PLC is on the standstill part and the ring is rotating. So there has to be wireless communication between the PLC and the ring. And that's what you see with this staggered blue line, which is not precise enough. So I needed something else, and therefore I chose a gyroscope, but that measures only angular velocity, so I needed to integrate its position, and due to drift, because of the integration process, that was not a viable solution on its own, so I needed to combine the PLC and gyroscope data, and the green position here shows the result of that combination, which is uh, more than good enough for now. Also here I indicated one turn, which is only 330 milliseconds when rotating at 3 RPM rotations per second. Film tension, you'd think that measuring the film tension with the load cell would be easy. Such components already exist, but that's not the case because the load cell will be rotating quite fast, and due to the rotation, there show virtual well, virtual measurements which are not really present on the film. So when going slow, we measure just this sine wave, which is the gravity acting upon our measurement system. And when going fast, there is also this yellow line, which is the centrifugal forces. And I needed to compensate those to get to the blue line, which is the now actual measurement. And all in all, there is only 50 gram force error on the load cell of an empty ring. So with no foil present, I measure within 100 gram force correct. So for the future work, all these subsystems are starting to work, each with their own challenges, but the integration still has a lot of work to do. And also the automation of the parameterization is really interesting because now I have to specify as this package has to be wrapped with 4 turns with this amount of tension, but we want to use the information available like the 3D camera to decide this wrapping profile. Also the investigation whether paper is a suitable alternative is really interesting, but we still need more time for that. And especially the wrapping performance for paper still has to be improved because now it only works at low speeds. So thank you for your attention, and now I'm open for your questions.
Oké. Ja. Ja, dus bedankt voor de presentatie. Heel interessant werk. Een belangrijke component bij die feedforward gaat natuurlijk uw model zijn dat je gebruikt om te voorspellen welke trekkrachten. Ja, ik ben nu in het Nederlands bezig eigenlijk. Okay. Dus an important component in your feedforward will be the model that you use to predict the tension forces. Did you somehow validate these? Or do you just use the computations in your control loop already?
So yeah, so these speed profiles that you see right here, they show up when you just use the motors as an encoder. So we know from that way that there is such a profile to be as expected. The way I derived those is just by looping around this shape inside and then doing some vector calculations. I calculate the vector component that represents the foil speed. So that is when you assume that there is exactly the package that you defined in the calculations. That's often not the case, but it gets quite close. And like in the middle, there is no film speed necessary, and that will be always the case. So just using this shape is already very interesting, and I scale it up and down by the use of my feedback loop. So my PID controller gives a multiplier for this shape, and that's the best I came up with up to today.
Okay, thank you. I'm looking around in the auditorium to see if there are additional questions. Yes. Martin will come, so you see some other faces as well.
Hello.
Hello.
Can you hear me?
Yep.
On one of your slides, you showed or you mentioned the use of a gyroscope to measure the angular velocity of the rings, of the ring. And based on the angular velocity, you integrate the angular velocity to obtain the position of the rings. Is there a reason why you didn't use, for example, an encoder, a multi-turn encoder, for measuring the position?
Yeah, so can you just turn off the microphone? Thank you. So I already used a couple of options. The main reason I don't use an encoder is that the ring is rotating. So if you have a suggestion where to put the encoder, please go ahead. But as far as I know, there is no nice way to put the encoder on around the rotating ring, because the information required is on the rotating part, and inside the rotating part there is the tunnel where the package has to pass, so you can't put it concentric. A couple of, I think years ago, I tried to put a second encoder, like a multi-turn encoder, onto the shaft of the servo motor that is driving the ring, and then I used Bluetooth to stream this information real time to the microcontroller on the ring. That was good, but not really as reliable as this solution. So that's why I went with the gyroscope, which is really not that bad. I only get 5 to 10 degrees of error after wrapping 5 to 10 turns. So that's within my tolerances.
Thank you.
Thank you.
Anyone else in question? Thank you. Thank you for your presentation.
and thank you for attending.
Ja, dat is graag gedaan. Maar.
Hopelijk. Ja, het zijn ook zware dagen voor u.
Ja, het is sowieso september is een super drukke maand. Maar dit valt nog allemaal mee qua, er zijn nog zwaardere. Dit is, ja,